Mars does not warn you. One crack in your suit and it is over before you even fully understand what is happening. 10 seconds to unconsciousness, less than that to the point of no return. And this is not even close to the most dangerous thing about living there. So what actually kills you on Mars? And is there any version of this where humans genuinely survive long enough to call it home? If you want to actually understand how the universe works, not just skim the surface of it, make sure to give this video a like. Now let's get started. Let's start with the atmosphere, because it is the foundation of almost every other problem on Mars, and most people fundamentally misunderstand what it actually means. The oxygen in the Martian atmosphere is present at a concentration of about 0.13%. You need roughly 21% oxygen at Earth standard pressure to breathe normally. Even if you could somehow concentrate the Martian oxygen and breathe it, the pressure is so low that your body could not absorb it. There is a concept in physiology called partial pressure. It is not just about the percentage of oxygen in the air, but about how much physical force that oxygen exerts, how hard it pushes against the membranes in your lungs. At Martian atmospheric pressure, the partial pressure of oxygen is essentially non-existent as far as your respiratory system is concerned. You would suffocate just as effectively in a room full of pure Martian air as you would in a complete vacuum. The mechanism would be different, the outcome would be the same. This means that every breath a human takes on Mars, for as long as humans live on Mars, must come from a closed system, a habitat with an artificial atmosphere, a suit with its own oxygen supply. There is no scenario in which humans walk around on the Martian surface, breathing ambient air, even with technological assistance, short of terraforming the entire planet, a process that would take centuries at minimum and possibly millennia. Every moment outside a pressurized structure is a moment of complete dependence on technology, not a preference, not a convenience, a requirement for continued existence. NASA's Perseverance rover, currently operating on the Martian surface, carries an instrument called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is designed to test whether oxygen can be produced from the Martian atmosphere by separating the oxygen atoms from carbon dioxide molecules through a process called solid oxide electrolysis, essentially heating carbon dioxide to extremely high temperatures and using an electrochemical reaction to split it. In 2021, MOXIE successfully produced about 5 grams of oxygen, enough to sustain a human for about 10 minutes. By 2023, it had demonstrated the ability to produce oxygen at varying times of day and in varying Martian seasons, proving the concept works under real Martian conditions. 5 grams in one demonstration. A resting adult human needs roughly 550 liters of oxygen per day, which translates to roughly 750 grams. An active adult needs considerably more. Scaled up, a MOXIE-style system capable of supplying a crew of 4 with breathable oxygen would need to be orders of magnitude larger than the current demonstration unit, and it would need to operate continuously, reliably, without failure for the entire duration of the mission. Any interruption in oxygen production that coincides with an exhaustion of stored reserves is not an emergency that can be managed. It is the end of the mission and the end of the crew. This is the baseline condition of life on Mars. Before we even talk about food or water or radiation or psychological pressure or the logistics of getting there, the most fundamental biological requirement, the thing your body does roughly 20,000 times a day without your conscious involvement, requires an elaborate, continuous, energy-intensive technological solution. Breathing on Mars is an engineering problem, a very hard one. Water is the next layer of the problem, and it is both more promising and more complicated than most people realize. We know Mars has water. This is not a hypothesis. It is a confirmed, well-documented fact established by multiple missions over multiple decades. The Mars Reconnaissance Orbiter has mapped enormous deposits of water ice just below the surface across much of the planet. The polar caps contain substantial quantities of water ice. The North Polar Cap alone is estimated to contain enough water ice that if it melted, it would cover the entire Martian surface to a depth of roughly 35 meters. Ground-penetrating radar data from the Marsis instrument aboard the Mars Express orbiter has identified what appear to be liquid water lakes beneath the South Polar ice cap. Though the exact nature of these features remains actively debated, they may be liquid water stabilized by dissolved salts at temperatures well below normal freezing point, or they may be something else. The debate continues. There is also water ice mixed into the regolith, the loose surface material, across wide areas of Mars, particularly at higher latitudes. Some regions have ice so close to the surface that future missions could potentially access it with relatively simple drilling or excavation equipment. Certain areas show evidence of recurring slope lineae, dark streaks that appear and fade seasonally on steep slopes, which were once interpreted as possible evidence of seasonal liquid water flows, though current research suggests they are more likely the result of dry granular flows or other non-water mechanisms. Mars is a place that constantly invites optimism and then qualifies it. But here is the thing about Martian water. Having water and accessing water are two entirely different problems, and the difference between them is enormous. Water ice buried beneath the surface or locked into polar ice caps does not flow from a tap. It has to be excavated, melted, filtered and processed at scale continuously, using equipment that must function reliably in an environment that will try very hard to break it. The Martian regolith is not like soil on Earth. It is dry, fine-grained, and in many regions heavily contaminated with perchlorates, chemical compounds that are toxic to humans at relatively low concentrations, and that would need to be rigorously filtered out of any water extracted from the surface. The perchlorate issue is not a minor technical footnote. It is a significant hazard that affects not just water processing but food production and any activity that involves contact with Martian dirt. And the energy required to melt and process ice on Mars is substantial. Mars receives about 43% of the solar energy per square meter that Earth does, due to its greater distance from the Sun. Solar panels on Mars are less efficient than on Earth, and they are further challenged by the famous Martian dust, fine particles that settle on surfaces over time, reducing panel efficiency. The global dust storms that periodically envelop the entire planet, lasting for weeks to months, can reduce solar energy availability to almost nothing for extended periods. The Opportunity rover, which was designed to operate for 90 Martian days, actually survived for nearly 15 years, but it was ultimately ended by a global dust storm in 2018 that coated its solar panels so thoroughly that the rover could no longer generate enough power to maintain operations. For a crewed habitat, a global dust storm is not an inconvenience. It is a crisis. Every system that depends on solar power, life support, heating, communication, water processing, food production, becomes endangered simultaneously at exactly the moment when the crew is most confined and most dependent on those systems. Nuclear power is the most viable solution, and NASA and other agencies have been developing compact nuclear fission systems specifically for this purpose. The Kilopower project, now evolved into the Fission Surface Power Program, aims to develop small reactors capable of providing around 10 kilowatts of continuous electrical power for surface operations. 10 kilowatts is enough to support a small crew in a minimal habitat. Scaling up to support a larger, more capable settlement requires proportionally more reactors, more complexity, more potential failure points. Everything on Mars connects to everything else. The atmosphere problem connects to the energy problem. The energy problem connects to the water problem. The water problem connects to the food problem. Pull on any one thread and the whole web moves. And we have not even gotten to the thing that might actually be the hardest problem of all. The one that does not show up in engineering diagrams or power budgets, but that has derailed more ambitious human endeavors than almost any technical challenge in history. Speaking of challenges that are harder than they look, if you want to understand just how quickly Mars would push the human body to its absolute limit, check out the video on the card above. It goes deep into exactly that. We explore why you wouldn't survive 1 year on Mars. Watch it after this one. It will give you a whole new layer of understanding for everything we are about to cover. The link is in the description and pinned on the comments because the next layer of the Mars problem, radiation, is something that changes the entire equation, not just for living on Mars, for getting there in the first place. And the numbers, when you actually look at them clearly, are genuinely alarming in a way that the public conversation about Mars colonization almost never fully acknowledges. What the radiation environment of deep space and the Martian surface does to the human body over time is not a solvable problem with current technology. It is a managed risk. And there is a very important difference between those two things, a difference that might ultimately determine whether humans can live on Mars at all, or only visit it briefly at enormous cost to their long-term health. That is exactly where we are going next. Let's talk about radiation, because this is the part of the Mars conversation that tends to get glossed over in the excitement of rocket launches and habitat designs and the grand vision of a human presence on another planet. It gets a paragraph in the risk assessment section of mission planning documents, and then the conversation moves on to something more photogenic. But radiation is not a footnote. It is arguably the single most serious biological obstacle to long-duration human presence beyond Earth's magnetic field. And the more carefully you look at the actual numbers, the more seriously you have to take it. Here on Earth, you are protected by two overlapping shields. The first is the magnetosphere, the vast magnetic bubble generated by Earth's rotating liquid iron outer core, which deflects the majority of charged particles streaming from the Sun and from deep space before they can reach the surface. The second is the atmosphere, roughly 10 metric tons of air above every square meter of ground, which absorbs and scatters the radiation that does manage to get through. Together, these two systems reduce your annual radiation exposure to a level your body can manage without significant long-term damage under normal circumstances. Mars has neither of these shields in any meaningful sense. Mars lost its global magnetic field billions of years ago, likely when its core cooled and solidified enough to stop generating the dynamo effect that produces a planetary magnetic field. Without that field, the solar wind, the continuous stream of charged particles flowing outward from the Sun, has been stripping away the Martian atmosphere for billions of years, which is a significant reason why the atmosphere is now so thin. Mars does have some localized magnetic anomalies, regions of magnetized crust, remnants of an ancient global field frozen into the rock, but these are patchy, regional, and nowhere near strong enough to provide meaningful protection for surface inhabitants. The Martian atmosphere, thin as it is, does provide some shielding, more than the complete vacuum of deep space, but the protection it offers is a fraction of what Earth's atmosphere provides. The result is that the radiation environment on the Martian surface is dramatically more intense than anything humans are exposed to on Earth, and significantly more intense than anything astronauts experience on the International Space Station, which still benefits from partial protection from Earth's magnetic field. The Curiosity rover, which landed in Gale Crater in 2012, carried a radiation assessment detector specifically designed to measure the radiation environment a human would experience on the Martian surface. The data it collected was sobering. A person standing on the Martian surface would be exposed to an average of roughly 233 microsieverts of radiation per day. To put that in context, the annual radiation limit for radiation workers in many countries is 20 millisieverts per year, which works out to roughly 55 microsieverts per day. On Mars, you would exceed that limit in less than 9 days. In a year on Mars, you would accumulate a radiation dose of roughly 85 millisieverts, more than 4 times the annual occupational limit, and approaching the career limit that NASA currently sets for its astronauts of roughly 600 millisieverts, though that limit itself is under review, and that is just the baseline surface dose. It does not include solar particle events, sudden, intense bursts of radiation from solar flares and coronal mass ejections that can spike radiation levels dramatically for hours or days at a time. On Earth, these events are largely invisible because the magnetosphere and atmosphere handle them. On Mars, a major solar particle event could deliver a life-threatening radiation dose in a matter of hours. The challenge is that while solar activity can be monitored and some warning can be provided, minutes to hours, depending on the nature of the event, the warning time is rarely enough to do more than shelter in place, which means Martian habitats need to be designed with dedicated radiation shelters, heavily shielded rooms where crew members can wait out a solar storm as a baseline safety feature, not an optional extra. The long-term health consequences of this radiation exposure are significant and well documented from research on Earth-based radiation exposure, from studies of nuclear workers and cancer patients who receive radiation therapy, and from monitoring of astronauts on long-duration missions aboard the International Space Station. The risks include elevated lifetime probability of cancer, particularly leukemia and solid tumors, as well as potential damage to the central nervous system that may affect cognitive function, memory, and behavior. Studies conducted on mice exposed to the types of high-energy charged particles found in the space radiation environment, particularly galactic cosmic rays, which are extremely difficult to shield against because of their high energy and penetrating power, have shown measurable cognitive impairment after exposure levels comparable to what an astronaut would receive on a Mars mission. The shielding problem for galactic cosmic rays is genuinely difficult in a way that has no easy solution. Unlike the relatively low-energy particles that make up most solar wind, galactic cosmic rays are atomic nuclei, primarily protons but also heavier nuclei including iron, accelerated to near-light speeds by supernova explosions and other energetic events in the galaxy. They are so energetic that they pass through most conventional shielding materials with relative ease. Worse, when they interact with shielding material, they can produce secondary radiation, a spray of particles generated by the collision that in some cases can be more biologically damaging than the original particle. The most effective shielding against galactic cosmic rays is mass, lots of it. Water is particularly good, as is polyethylene, which is rich in hydrogen atoms that are effective at slowing energetic particles. Underground habitats, buried under meters of Martian regolith, would provide substantially better protection than surface structures. This is one of the stronger arguments for building Martian habitats underground. Either in purpose-built excavations or in lava tubes, the long underground tunnels formed by ancient volcanic activity that are known to exist on Mars in substantial numbers and at potentially enormous scale. Some Martian lava tubes, based on analysis of surface features, may be hundreds of meters wide and potentially kilometers long, large enough to contain entire cities under a natural rocky ceiling that would provide excellent radiation shielding as well as protection from temperature extremes and micrometeorite impacts. The idea is scientifically credible and is taken seriously by planetary scientists and mission planners. The engineering challenge of accessing, assessing, and building inside them is formidable but not obviously impossible. But underground habitats introduce their own suite of problems, psychological ones primarily, and we will get to those. First, let's finish the radiation picture, because there is one more piece that does not get discussed nearly enough: the journey itself. Getting to Mars takes roughly 6 to 9 months with current propulsion technology, depending on the specific trajectory and the alignment of the planets at departure. During that transit, the crew is in deep space, completely beyond Earth's magnetosphere, with no atmospheric shielding, exposed to the full intensity of both the solar particle environment and the galactic cosmic ray flux. The transit radiation dose alone, each way, is estimated at roughly 300 millisieverts under average solar conditions. A round trip, 6 to 9 months out, a surface stay of roughly 500 days, waiting for the planets to realign for the return journey, and 6 to 9 months back would expose a crew member to a total mission radiation dose that approaches or potentially exceeds current career limits, depending on solar activity during the mission. This is why some mission architects have proposed one-way missions, permanent settlement rather than return trips, as a way of at least halving the transit radiation dose. It is also why there is significant interest in nuclear propulsion systems that could reduce transit time to perhaps 45 to 90 days, dramatically cutting the deep space radiation exposure. The nuclear thermal propulsion concept, which uses a nuclear reactor to heat propellant and expel it at much higher velocities than chemical rockets can achieve, has been studied for decades and is currently being actively developed by NASA and the Department of Defense. It is not science fiction. The NERVA program in the 1960s and 70s demonstrated the basic technology, but it has never been flown, and bringing it to operational readiness for a crewed Mars mission is a substantial engineering and political undertaking. The radiation problem does not have a clean solution with current or near-term technology. It has a collection of partial mitigations, shielded habitats, radiation shelters for solar events, careful mission timing to avoid periods of maximum solar activity, pharmaceutical countermeasures that are still largely in development, and a frank acceptance that Mars settlers will carry a measurably elevated lifetime cancer risk that cannot be fully engineered away. This is not defeatism, it is honesty, and honesty about the real costs and risks is the foundation of any serious plan for human presence on Mars. Now let's talk about the human body itself, because radiation is attacking it from the outside, but Mars is also attacking it from the inside, in ways that are subtler, slower, and in some respects just as serious. The fundamental problem is gravity. Mars has a surface gravity of 3.72 meters per second squared, about 38% of Earth's, which sounds almost manageable. 38% of Earth's gravity means you would weigh less than half as much on Mars as you do on Earth. You could jump higher, carry heavier loads relative to your body weight, move with less physical effort. In the short term, that sounds like a benefit, and in the immediate practical sense it is, but your body did not evolve for 38% gravity. It evolved for 100% gravity. Every system in your body, your skeleton, your muscles, your cardiovascular system, your vestibular system, your fluid distribution, your immune response is calibrated for a specific gravitational load that has been essentially constant throughout the entire evolutionary history of your species. Take that load away, or even significantly reduce it, and the body begins to change, and not in beneficial ways. We know this from extensive research on astronauts aboard the International Space Station where gravity is effectively zero, microgravity as it is called, because the station and everything inside it are in continuous freefall around Earth. In microgravity, bone density decreases at a rate of roughly 1 to 2% per month in the most affected areas, the load-bearing bones of the lower body and spine. Muscle mass decreases. The cardiovascular system adapts to the reduced demands of pumping blood against gravity, and the heart can lose mass over time. Fluid shifts upward in the body, causing the characteristic puffy face that astronauts develop within days of arrival at the station, as well as elevated intracranial pressure that has been linked to vision problems, a condition called spaceflight-associated neuroocular syndrome, or SANS, which is currently one of the more concerning long-term health findings from ISS research. The immune system behaves differently in space. Latent viruses, including herpes viruses that most adults carry in a dormant state, tend to reactivate in the space environment. Mars gravity is not zero gravity. It is 38%, which is meaningfully different from microgravity and may be significantly better for long-term health. But we do not know how much better, because no human being has ever lived in a sustained reduced gravity environment between 0 and 1. The International Space Station gives us excellent data on zero gravity. Earth gives us excellent data on 1 gravity. There is a large and scientifically critical gap in between, and Mars sits squarely in that gap. Whether 38% gravity is enough to prevent the most serious long-term physiological changes that occur in microgravity, or whether it merely slows them, is a question that cannot be answered with current data. It can only be answered by humans actually going to Mars and being monitored over extended periods. This uncertainty has profound implications for the question of whether Mars can sustain a permanent human population, not just visitors on finite missions, but people who intend to spend their lives there, people who want to have children there. Because the question of reproduction in Martian gravity, of whether human development from conception through birth and childhood can proceed normally at 38% of Earth's gravity, is one that has received surprisingly little public attention, given its fundamental importance to the concept of a self-sustaining colony. The biological processes of reproduction and development are exquisitely sensitive to physical forces. Fluid dynamics, cell division, organ development, bone formation, cardiovascular development, all of these processes occur in the context of Earth's gravity and have been shaped by it over billions of years of evolution. Whether a fetus can develop normally in a Martian womb, whether a child's skeleton and cardiovascular system and vestibular system can develop normally in Martian gravity, whether a person born on Mars could ever safely visit Earth without experiencing Earth's gravity as crushingly intense, these are questions without answers, and they are not hypothetical edge cases. They are central to the feasibility of a permanent human presence on Mars. Centrifuges can provide artificial gravity in space, rotating structures that use centrifugal force to simulate gravitational load. On a space station, you could in principle build a rotating section that provides Earth-standard gravity for sleeping, exercise, and critical biological processes. On a planetary surface, centrifuges can be used for exercise, essentially fast-spinning exercise equipment that imposes higher gravitational loads on the body, but you cannot put the entire habitat on a centrifuge. You cannot make the whole surface of Mars spin faster. The gravity you experience when you walk out the door is the gravity you get, and on Mars that is 38%. The physiological unknowns around Martian gravity represent a fundamental gap in our understanding of whether Mars can be a home for humanity in any deep, multi-generational sense. It is possible that the human body adapts to Martian gravity in ways that are sustainable and manageable, It is also possible that Martian gravity is insufficient to maintain the health of adults over decades and catastrophically insufficient for the development of children. We simply do not know. And finding out requires sending humans to Mars, which itself requires solving all the other problems first. This is one of the most honest things you can say about Mars colonization. The questions that most need answering cannot be answered until you are already there. The risks that most need quantifying cannot be quantified without exposing people to them. The mission is, at a fundamental level, a leap into incomplete knowledge, a willingness to go and find out, knowing that some of what you find out might be that it is harder or in some respects impossible in ways that were not fully anticipated. That is not necessarily an argument against going. Some of the most important things humanity has ever done have involved leaping into incomplete knowledge. But it is an argument for going with clear eyes, for not letting the inspirational framing of multiplanetary civilization obscure the genuine, deeply serious, currently unresolved challenges that stand between where we are now and a human being waking up on Mars on an ordinary Tuesday and going about their day. And the challenges we have covered so far, the atmosphere, the water, the radiation, the gravity, are the physical ones, the measurable ones, the ones that show up in data and equations and engineering specifications. There is another category of challenge waiting ahead that is harder to quantify and in some ways harder to solve. The challenge of what happens inside a human mind when it has been confined, isolated, irradiated, and cut off from Earth for years at a time. When the people you love are so far away that a message takes up to 24 minutes to reach them each way. When the sky above you is the wrong color. When everything familiar is millions of kilometers behind you and there is no coming back for years. The psychological reality of Mars is where the missions gets personal, and it is where the story gets, in some ways, the most interesting. That is exactly where we are headed next. There is a moment that every long-duration astronaut describes, usually sometime in the middle third of their mission, when the novelty has worn off and the end is still too far away to feel real, a kind of flatness, a grey settling in, not depression necessarily, though depression is a documented risk in isolated, confined environments, but something more like a slow erosion of the sharp edges of experience. Food starts to taste the same. The view outside, if there is one, stops registering as remarkable. The people around you, who you respect and probably like, begin to grate in ways that feel disproportionate to the actual friction. Small annoyances accumulate into something heavier. The routines that were designed to provide structure start to feel like walls. This is what researchers who study isolated and confined environments call the third quarter phenomenon. The psychological low point of a long mission tends to occur not at the beginning, when the challenge is new and adrenaline is still present, and not at the end, when the finish line is visible and motivation surges. It hits in the third quarter, when you are past the halfway point, still far from done, and the psychological reserves that carried you through the first half are genuinely depleted. On a mission to Mars, the third quarter might fall somewhere in the middle of the surface stay, after the drama of landing, after the initial excitement of being on another planet, but long before any realistic return home is possible. And unlike an astronaut on the International Space Station, who is never more than a few hours from Earth, in an emergency evacuation, a person on Mars has no such option. There is no emergency return. The orbital mechanics that govern the journey home are fixed by the positions of the planets, and those positions change on timescales of months and years. If you are on Mars and something goes wrong, medically, psychologically, interpersonally, you deal with it there. There is nowhere else to go. The implications of this for mission planning and crew selection are profound, and researchers have been studying them for decades using analog environments. places on Earth that simulate imperfectly but usefully some of the conditions of an isolated long-duration space mission. The Mars Desert Research Station in Utah, the High Seas habitat in Hawaii, where multiple crews have spent periods of up to a year in simulated Mars isolation. The Concordia Research Station in Antarctica, where small international crews overwinter for months in complete isolation, in darkness, at temperatures that make going outside a significant undertaking. The Russian Mars 500 project, which simulated a 520-day Mars mission in a sealed facility in Moscow with a crew of 6 who lived and worked in conditions designed to replicate the isolation and communication delays of a real Mars mission. The data from these studies is illuminating and occasionally uncomfortable. Crews in long-duration isolation consistently show predictable patterns of psychological and interpersonal change. Sleep disruption is nearly universal. The circadian rhythm, which is calibrated to Earth's 24-hour day, has to adapt to Mars's slightly longer sol of 24 hours and 37 minutes. And while that difference sounds trivial, it compounds over time in ways that affect sleep quality, mood, and cognitive performance. The Mars 500 study found that some crew members developed significant sleep disruption and sedentary behavior over the course of the mission, with one participant showing patterns consistent with chronic sleep deficiency. Cognitive performance, the ability to perform complex tasks, respond quickly, maintain attention, degrades under conditions of fatigue, isolation, and monotony in ways that are well documented and that cannot be fully compensated for by training or motivation. Interpersonal conflict is the other major documented risk. In any small, isolated group, interpersonal dynamics become enormously amplified. Quirks that would be trivial in normal social life, a particular way of speaking, an approach to shared tasks, a set of habits around food or noise or personal space, become significant in an environment where there is no escape, no change of scenery, no new faces, no ability to simply leave and come back when things have cooled down. The conflict does not have to be dramatic to be damaging. Sustained, low-level friction in a small crew is corrosive to cohesion, to performance, and to the psychological health of everyone involved. And it is almost guaranteed to occur on a mission long enough to reach Mars. NASA and other space agencies have invested heavily in crew selection, group dynamics research, and interpersonal conflict resolution protocols, specifically because they know this. The selection of crew members for long-duration missions goes far beyond technical competence. It involves extensive psychological assessment, evaluation of conflict resolution style, assessment of emotional regulation, and increasingly sophisticated attempts to model how specific combinations of people will interact under stress over extended periods. The science of putting the right people together is real and is taken seriously, but it is still far from perfect. Human beings are complex, and the conditions of a Mars mission are unlike anything in ordinary human experience, which means that even the best prepared crew will encounter psychological territory that their training did not fully anticipate. The communication delay compounds everything. At minimum conjunction, when Earth and Mars are closest, roughly 55 million kilometers apart, a radio signal traveling at the speed of light takes about 3 minutes to make the one-way trip. At maximum separation, when the two planets are on opposite sides of the Sun and nearly 400 million kilometers apart, the one-way delay stretches to over 22 minutes. The average over the course of a Mars surface mission is somewhere around 12 to 14 minutes each way, meaning a back-and-forth exchange of any kind takes a minimum of 25 minutes under good conditions and up to 45 minutes or more at other times. Real-time conversation with anyone on Earth is impossible. A phone call home, the thing that sustains people through long separations in every other context of human life, is not available. Communication happens through messages, video recordings, emails. You speak your piece, send it into the void, and wait half an hour or more for a response to arrive. Mission Control cannot talk you through a crisis in real time. If a medical emergency occurs, the doctor on Earth who receives the alert cannot ask you follow-up questions and hear your answers in the same conversation. Everything is asynchronous. Everything is delayed. Everything that would normally flow in real time has to be translated into a format that can survive a 20-plus minute interruption in the middle. For the crew, this has a specific psychological consequence that is often underestimated. It is not just the loneliness, though the loneliness is real and documented. It is the experience of operating, genuinely, without a safety net, without the reassurance that someone on Earth is watching in real time and can intervene. On the International Space Station, mission control in Houston or Moscow is always on. Astronauts can speak to ground teams in real time. Decisions can be made collaboratively, instantly. On Mars, the crew is effectively autonomous. Every decision of any consequence, medical, engineering, operational, has to be made by the people on the ground. Not the ground in Houston, the ground on Mars, the crew itself. This is actually one of the strongest arguments for crews of diverse expertise. A crew where every member brings depth in multiple disciplines, not just their primary specialty. A crew doctor who also understands mechanical engineering. A geologist who can perform emergency surgery if needed. An engineer who can make pharmacological decisions in a crisis. The concept of the autonomous crew, capable of handling any foreseeable emergency without real-time support from Earth, is a fundamental design requirement for a Mars mission, and it places demands on individual crew members that go well beyond what astronauts on shorter missions have historically needed to meet. Then there is the question of what the mind does with a sky that is the wrong color. This sounds almost trivial. It is not. Human beings are deeply, evolutionarily sensitive to light and color, and the rhythm of day and night, our mood, our cognition, our hormone cycles, our sleep architecture, all of these are entrained to the spectrum and intensity of sunlight on Earth. The Martian sky is not blue, it is a butterscotch tan on clear days, shifting toward pink and even bluish near the sun at sunset, due to the scattering of light by fine dust suspended in the thin atmosphere. The sun in the Martian sky is smaller and fainter than it appears from Earth, about 60% as bright. Martian days, as mentioned, are slightly longer than Earth days. Martian seasons are longer because Mars takes 687 Earth days to complete one orbit of the Sun. None of these differences are individually catastrophic, but they accumulate. The perceptual environment of Mars is subtly but persistently wrong relative to everything the human nervous system has been calibrated for by millions of years of evolution on a specific planet with a specific sky and a specific sun at a specific distance. Whether and how those subtle wrongnesses compound over years of exposure is not well understood, because no human has ever experienced them. What we do know from research on light and mood on Earth is that environmental light has profound effects on psychological well-being, and that disruptions to natural light cycles, the kind of disruption that shift workers and people in high-latitude winters experience, are associated with increased rates of depression, cognitive impairment, and sleep disorders. On Mars, the disruption would be permanent, total, and unlike anything on Earth. Habitat design will attempt to compensate for this. Full-spectrum lighting systems tuned to simulate Earth daylight conditions. Windows where structurally and radiation safety-wise feasible to provide views of the exterior. Green spaces, plants growing in pressurized indoor areas that provide visual and olfactory cues of living Earth environments. Music, art, personal mementos virtual reality environments that simulate familiar Earth settings. All of these are real considerations in long-duration habitat design and are being actively researched. But compensation is not the same as resolution. You can mitigate the psychological effects of the wrong sky. You cannot make it the right sky. There is something deeper here, though, that sits underneath all the specific psychological challenges, something that is harder to name but that matters enormously. It is the question of meaning, of why you are there, of what the whole thing is for. Human beings are remarkably capable of enduring extreme hardship when they are convinced of the purpose behind it. The history of exploration, of scientific research in extreme environments, of human endeavor in the face of genuine risk, is full of examples of people who sustained themselves through conditions that should have broken them because the mission, whatever it was, gave the suffering a frame that made it bearable. Ernest Shackleton's crew, stranded on the ice of Antarctica for 20 months after their ship was crushed, maintained extraordinary cohesion and morale largely because of Shackleton's leadership and the crew's collective commitment to survival as a shared goal. The early cosmonauts and astronauts endured isolation, physical stress, and genuine danger because they understood themselves to be part of something historically significant. The scientists who overwinter at Antarctic research stations, months of darkness, extreme cold, complete isolation, consistently report that the scientific work gives the experience meaning that sustains them through the hardest parts. For a Mars crew, the meaning is built in. You are the first human beings on another planet. Whatever else happens, that fact is permanent and indelible. You are doing something that billions of people have imagined and no one has yet done. The weight of that is real, and for many people it would be enough to sustain almost any level of hardship, but sustaining a permanent colony, not the first crew of explorers, but the 100th, the 1000th, the people who are born on Mars and grow up there and live their whole lives there, that requires a different kind of meaning. Not the meaning of being first, which is a one-time event, but the meaning of building something that matters. A society, a culture, a civilization. The question of what values, what institutions, what shared stories and practices and ways of being together would constitute a genuinely Martian human culture. That is not an engineering question. It is a question for artists and philosophers and anthropologists and ordinary people living ordinary lives in extraordinary circumstances. And it is, in its own way, one of the most interesting questions that Mars raises. Not what temperature is it on the surface, not how do you extract water from the regolith, not what is the radiation dose in a lava tube, but what does it mean to be human on another planet? What of Earth's culture do you carry with you, and what do you leave behind? What new things do you discover about human nature when it is operating in conditions it has never faced before? What kind of people does Mars make? These questions do not have answers yet. They are waiting for the people who go, and the people who go will answer them not in papers or mission reports, but in the texture of their daily lives, in the institutions they build, and the conflicts they resolve, and the children they raise, and the stories they tell about themselves and each other, and the strange, cold, radiation-soaked, butterscotch-skied world they have chosen to call home. But before any of that can happen, before the psychology and the culture, and the question of what it means to be human on Mars, there are some brutally practical problems that need solving first. Problems of food, of agriculture, of whether you can actually grow enough calories in Martian soil under Martian conditions to keep a human being alive without a continuous resupply chain from Earth. Because the moment you stop being resupplied from Earth is the moment Mars has to feed itself, and what that actually requires, the biology, the chemistry, the engineering, The sheer scale of the agricultural infrastructure needed to feed even a small permanent settlement is one of the most underappreciated challenges in the entire Mars colonization picture. And there is one specific detail about Martian soil that changes everything. One chemical compound present across wide areas of the Martian surface that makes agriculture on Mars not just difficult, but potentially impossible using any straightforward approach. Something that the excitement around Mars colonization almost never fully grapples with. That is exactly where we are going next, and the answer is going to make you look at the whole project very differently. If you are enjoying this journey, make sure to give this video a like. Every video here is built on real science, real missions, real data. Hit subscribe and turn on notifications so you never miss one. Let's talk about what it actually takes to get a human being to Mars, not the inspirational version, the engineering version, because the moment you start looking at the specific numbers, the mass, the energy, the logistics, the sequencing, you develop a very different appreciation for why this has taken as long as it has, and why the decisions being made right now about rocket design and mission architecture are going to determine whether humans reach Mars in the 1930s or the 1950s, or possibly not at all within any time frame that currently living people will see. The fundamental problem of getting to Mars is one of energy, not fuel exactly, though fuel is part of it, but the deeper concept that physicists call delta V. Delta V is the measure of how much a spacecraft needs to change its velocity to get from one place to another. Every maneuver in space, accelerating away from Earth, adjusting trajectory mid-journey, slowing down to enter Mars orbit, descending to the surface, costs delta V, and delta V costs propellant, and propellant has mass, and mass costs more propellant to launch from Earth. This circular relationship, where more mass requires more propellant, which has mass of its own, which requires still more propellant, is described by the Tsiolkovsky rocket equation, one of the most important and most unforgiving equations in all of engineering. It means that the relationship between the mass you want to deliver somewhere and the mass you need to launch from Earth is not linear. It is exponential. Every additional kilogram you want to deliver to the Martian surface requires dramatically more than one additional kilogram of propellant and rocket structure on the launch pad. The most efficient trajectory from Earth to Mars, the one that requires the least delta V and therefore the least propellant, is called a Hohmann transfer orbit. It involves launching when Earth and Mars are in a specific geometric relationship, following an elliptical arc that takes roughly 6 to 9 months depending on the specific trajectory, and arriving at Mars when the planet has moved to intercept that arc. The window for this optimal trajectory opens approximately every 26 months when Earth and Mars are properly aligned. Miss the window, and you wait another 26 months, or you use a less efficient trajectory that costs significantly more propellant and therefore significantly more launch mass. This 26-month cycle is a fundamental rhythm of Mars mission planning, and it creates a kind of drumbeat of urgency that shapes the entire logistics chain. If your hardware is not ready when the window opens, you are not going to Mars on that cycle. You wait, and waiting costs money, momentum, and in some cases careers and political will. The mass that needs to reach Mars for a crewed mission is staggering. A study published by NASA in the early 2010s as part of the design reference architecture for Mars. The agency's detailed engineering blueprint for a human Mars mission estimated that a 6-person crew on a roughly 500-day surface mission would require on the order of several hundred metric tons of hardware delivered to the Martian surface. That includes the transit vehicle, the surface habitat, the power systems, the life support equipment, the scientific gear, the ascent vehicle needed to get the crew back off Mars and into orbit. and a portion of the consumables, food, water, atmosphere, not produced locally. The exact figure depends heavily on the specific mission design and the degree to which local resource utilization, extracting water, producing propellant from the Martian atmosphere, offsets the need to bring things from Earth. For context, the Saturn V rocket, the most powerful rocket ever successfully flown, the machine that sent the Apollo astronauts to the Moon, could deliver roughly 130 metric tons to low Earth orbit. Getting mass from low Earth orbit to the Martian surface requires additional propulsion, reducing that number dramatically. The point is that a human Mars mission requires a launch and delivery capability that dwarfs anything that has ever actually flown. This is where SpaceX's Starship enters the picture, and it is worth understanding what Starship actually is and why it matters so specifically to the Mars problem. Starship is a fully reusable two-stage launch vehicle consisting of a massive first stage called the Super Heavy Booster and an upper stage called Starship. Confusingly, both the whole vehicle and the upper stage share the name. The combined vehicle stands roughly 121 meters tall, making it the largest rocket ever built. The Super Heavy Booster is powered by 33 Raptor engines burning liquid methane and liquid oxygen. The Starship upper stage carries up to 6 Raptor engines in its vacuum-optimized configuration. The target payload capacity to low Earth orbit is on the order of 100 to 150 metric tons in expendable mode, with reusability potentially enabling even greater effective throughput through rapid relaunch of the same vehicle. The choice of liquid methane as propellant is not arbitrary. It is a direct consequence of the Mars mission architecture. Methane can be synthesized on Mars using the Sabatier reaction, which combines carbon dioxide, abundant in the Martian atmosphere, with hydrogen to produce methane and water. The hydrogen can be obtained by electrolyzing water extracted from the Martian subsurface. The resulting methane and liquid oxygen, the oxygen produced either from electrolysis or from the MOXIE-style carbon dioxide splitting process, constitute the propellant that a Starship on Mars would need to refuel for the return journey to Earth. This concept, called in situ resource utilization or IRU, is central to SpaceX's Mars architecture. Rather than bringing all the return propellant from Earth, which would require launching an enormous additional mass, you produce it on Mars using Martian resources and energy. The math only works if you can reliably produce propellant on Mars at scale, which requires infrastructure, energy, and time, ideally delivered to Mars on unmanned precursor missions before the crew arrives. The full SpaceX Mars architecture envisions a fleet of Starships, not one or two but potentially dozens, launching in each 26-month window, carrying hardware, propellant, supplies, and eventually people. The first missions would be robotic, delivering power generation equipment, propellant production infrastructure, and early habitat components to the Martian surface. Once enough infrastructure is in place to support human arrival and to begin propellant production for the return journey, crewed missions would follow. The crew would not arrive until the return propellant is already waiting for them. This is not a new idea. The concept of pre-deploying assets on Mars before the crew arrives has been central to serious Mars mission planning for decades. But SpaceX has built its entire rocket design around making this specific architecture work, which gives the methane propellant choice and the full reusability goal a clarity of purpose that is genuinely impressive from an engineering standpoint. The challenge is that, as of 2025, Starship has not yet completed a full successful mission demonstrating all the capabilities required for Mars. The integrated vehicle has flown several test flights with progressively better results. The first integrated flight in April 2023 ended in a vehicle breakup before stage separation. The second, in November 2023, achieved stage separation, but both stages were lost, and subsequent tests demonstrated increasingly successful outcomes, including controlled returns and catch attempts of the Super Heavy booster. But the gap between the test flight envelope and the full operational capability required for a Mars mission, including propellant transfer in orbit, long-duration coast with cryogenic propellants, precise landing on an unimproved Martian surface, and reliable operation of the entire system in the deep space environment is still substantial. Each test provides data. Each successful demonstration narrows the gap. But the engineering work remaining is significant, and timelines in rocket development have a well-established tendency to expand rather than contract. NASA's own path to Mars runs through the Artemis program, the agency's initiative to return humans to the Moon as a proving ground for the technologies and operational experience needed for Mars. The logic is sound in principle. The Moon is close enough that problems can be addressed relatively quickly, communication delays are measured in seconds rather than minutes, and emergency return is feasible. Operating on the lunar surface in spacesuits, building and operating a lunar gateway station in orbit around the Moon, testing life support systems and surface mobility and in situ resource utilization in a real extraterrestrial environment. All of this builds the knowledge base and operational confidence that a Mars mission will require. The lunar South Pole, where NASA is targeting its Artemis landing sites, has regions of near-permanent shadow where water ice deposits have been confirmed, making it a relevant analog for the water extraction challenges that will be central to Mars surface operations. But Artemis has also experienced significant delays and cost overruns that are relevant to any honest assessment of the path to Mars. The Space Launch System, NASA's own heavy-lift rocket that forms the core of the Artemis architecture, has cost far more and taken far longer to develop than originally projected. The Orion capsule, the crew vehicle for Artemis, has been in development for 2 decades. The politics of large government space programs, subject to changing administrations, congressional budget cycles, and competing priorities, introduce a kind of uncertainty that is fundamentally different from the operational uncertainties of the mission itself. A Mars mission architecture that depends on sustained political will and consistent funding over a period of decades is inherently more fragile than one that can be executed more quickly or that is driven primarily by a private company with a clearer, singular focus. The commercial approach, SpaceX building Starship primarily with private funding toward a specific architectural goal, is in some respects more focused and agile than the government program model, but it carries its own risks. Private companies are subject to financial pressures, market conditions, and the specific vision and priorities of their leadership in ways that can also shift. The fact that SpaceX's Mars architecture depends on Starship succeeding commercially as a launch vehicle, generating revenue from satellite launches, NASA contracts, and other customers that funds the ongoing development work, means that the Mars program is in some ways a derivative of the commercial launch market in ways that introduce their own uncertainties. The honest answer to the question of when humans will go to Mars is that it depends. It depends on Starship achieving its full operational capability on a timeline that current testing can only partially illuminate. It depends on NASA's Artemis program successfully establishing lunar operations that build the necessary experience base. It depends on political will in the United States and potentially in other countries and in the private sector sustaining the focus and funding required over a timeline of years to decades. It depends on solving the specific engineering challenges of Mars entry, descent, and landing, which for large, heavy payloads like crewed habitats involves aerodynamic and propulsion challenges that have never been attempted at the required scale, and it depends on solving all the life support, radiation protection, food production, and medical challenges that we have been discussing throughout this video to a degree of reliability that is genuinely sufficient for human lives. SpaceX has publicly targeted the late 2020s for the first uncrewed Starship missions to Mars, with crewed missions potentially following in the early 2030s. NASA has discussed human Mars missions in the 2030s to 2040s timeframe. Independent analysts range from cautiously optimistic to significantly more skeptical about both of these timelines. The consensus view among people who have thought carefully about the engineering and logistics is that the 2030s is technically possible for a first crewed landing, but that it would require a sustained execution of extremely complex development programs at a pace and consistency that has rarely been achieved in aerospace history. The 2040s is more broadly considered achievable under a wider range of assumptions. Beyond that, the timelines become sensitive to factors that are genuinely unpredictable. None of this is discouraging if you understand it correctly. The fact that the timeline is uncertain does not mean the mission is impossible. The history of human spaceflight is a history of missed deadlines and unexpected breakthroughs in roughly equal measure. What the uncertainty should produce is not pessimism but realism, a clear-eyed understanding of how much work remains, why that work is hard, and what would have to go right for the optimistic timelines to hold. Because the work is being done, the rockets are being built and tested, the life support technologies are advancing, the in-situ resource utilization concepts are being validated by rovers and landers operating on Mars right now. The scientific understanding of the Martian environment, its radiation, its geology, its subsurface water, its atmospheric chemistry has never been better, and it continues to improve with every mission. The gap between where we are and where we need to be is real, but it is a gap that is being actively, seriously, and in many cases brilliantly worked on by thousands of engineers and scientists around the world. And there is one more dimension of the Mars challenge that has not yet been fully addressed. One that sits above the engineering and the biology and the logistics and shapes all of them simultaneously. The economic dimension. Who pays for all of this? How much does it actually cost? And what, if anything, does Mars offer in return? Not in terms of inspiration or scientific discovery, which are real but difficult to price, but in terms of tangible economic value that could sustain the enormous ongoing investment that a permanent Mars presence would require. Because ultimately, the question of whether humans live on Mars is not just a question of whether it is physically possible. It is a question of whether enough people, with enough resources and enough sustained commitment, decide that it is worth doing. And what makes something worth doing at the scale of civilizations and centuries is one of the deepest questions the Mars project raises. That question, the economics, the geopolitics, the question of who Mars belongs to and who gets to decide what happens there, is the layer of the problem that ties everything else together. Money is not a romantic subject. It does not inspire the kind of awe that comes from looking at a photograph of the Martian surface, rust-red and ancient and impossibly vast. It does not carry the emotional weight of imagining a human being standing on another planet for the first time. But money, or more precisely the question of who funds what, why, and for how long, is the invisible architecture beneath every space program that has ever existed. And for Mars, it is the constraint that makes every other constraint harder, because every solution to every problem we have discussed costs money. Enormous, sustained, multi-decade quantities of money, and the sources of that money are neither infinite nor unconditional. The Apollo program, which landed 12 human beings on the moon between 1969 and 1972, cost approximately $25 billion in 1960s currency, which translates to somewhere in the range of $250 to $300 billion in contemporary terms. Depending on the inflation adjustment method used, it consumed at its peak roughly 4% of the entire United States federal budget. It employed around 400,000 people directly, and it was sustained for roughly a decade before the political and economic calculus shifted and the last 3 planned lunar landing missions were cancelled. Apollo was one of the most expensive peacetime undertakings in American history, and it ended not because the moon had been conquered, but because the political will and the public attention that had sustained it ran out. Mars is harder than the moon in almost every dimension. The distances are greater, the mission durations are longer, the mass that needs to be delivered is larger, the life support requirements are more stringent. The communication delays change the operational model fundamentally, and the cost, while genuinely difficult to estimate because it depends so heavily on the specific architecture, the degree of reusability achieved, the extent of international partnership, and the role of commercial providers is almost certainly larger in absolute terms than Apollo, even if the fraction of GDP required is smaller due to the growth of the global economy since the 1960s. NASA's own internal cost estimates for a human Mars mission, produced at various points over the past several decades, have ranged from a low of around $50 billion for the most streamlined architectures to several $100 billion for more comprehensive mission designs. The RAND Corporation and other independent analysts have generally come in at the higher end of those ranges when examining the full system costs. SpaceX has been characteristically bullish about cost reduction through reusability. Elon Musk has at various points suggested that Starship development and early Mars missions could be accomplished for tens of billions of dollars rather than hundreds of billions, but these estimates are based on assumptions about Starship's reusability and launch cadence that have not yet been demonstrated at scale, and independent engineers have generally viewed them as optimistic. The funding model matters as much as the total cost, because a Mars program that requires a massive upfront investment before generating any return is a very different economic proposition from one that can be built incrementally, with each phase generating some value that partially funds the next. NASA's current approach, building the capabilities needed for moon operations first, through Artemis, with Mars as a longer-term destination, is partly driven by this logic. The moon offers near-term scientific returns, technology demonstration opportunities, and political milestones that can sustain funding through budget cycles in ways that a program with no near-term deliverables cannot. The international dimension is significant and often underappreciated. No single nation has funded a moon landing since Apollo, though China's Chang'e program has achieved impressive robotic lunar exploration and is working toward crewed lunar missions, and the Artemis program has attracted international partners including the European Space Agency, the Japan Aerospace Exploration Agency, the Canadian Space Agency, and others. A Mars mission with genuine international partnership could distribute the cost across multiple national budgets, build political resilience into the program by giving multiple countries a stake in its success, and potentially draw on scientific and engineering talent from a broader pool. The International Space Station, despite its enormous cost and the political complications of managing a multinational program, demonstrated that sustained international collaboration on a complex space infrastructure project is possible. Mars could follow a similar model, though the geopolitical landscape of the 2020s and 30s, with increasing strategic competition between the United States and China in space, complicates the picture in ways that make genuine collaborative Mars exploration both more necessary and more politically difficult than it might otherwise be. China's own deep space ambitions are relevant here. The China National Space Administration has publicly stated goals for robotic Mars exploration. The Tianwen-1 mission in 2021 successfully delivered an orbiter, lander and rover to Mars, making China only the second nation after the United States to operate a rover on the Martian surface, and has discussed longer-term ambitions including Mars sample return and eventually crewed Mars missions. The timeline for Chinese crewed Mars missions is not publicly detailed with the same specificity as NASA or SpaceX plans, but the demonstrated technical capability and the pace of China's space program development suggest that it is a serious long-term goal rather than a distant aspiration. A scenario in which both the United States and China are independently working toward crewed Mars missions creates a competitive dynamic that could either accelerate both programs, as Cold War competition accelerated Apollo, or create political complications around the legal and governance frameworks that would need to be established for a permanent human presence on Mars. The legal framework question is genuinely unresolved and has significant practical implications. The Outer Space Treaty of 1967, which forms the foundation of international space law and has been signed by over 100 nations, establishes that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty. No nation can claim Mars. But the treaty was written before private commercial space activity was a realistic prospect, and its provisions regarding the rights of private entities to extract and use resources from celestial bodies are ambiguous in ways that have generated substantial legal debate. The United States passed the Commercial Space Launch Competitiveness Act in 2015, which explicitly grants American citizens the right to own resources they extract from outer space, essentially asserting that while no one can claim the territory, you can claim the stuff you dig up. Several other countries have passed similar legislation, but there is no binding international consensus on these questions, and the absence of a clear legal framework for who gets to do what on Mars, who can build where, who owns what infrastructure, how disputes between settlers or between national programs are resolved, is a governance gap that will need to be addressed before a permanent human presence becomes a realistic near-term prospect. The Artemis Accords, first established in 2020, represent one attempt to build a multilateral framework for responsible space exploration, including provisions around transparency, interoperability of systems, release of scientific data, and the avoidance of harmful interference between missions. As of 2025, more than 40 nations had signed the accords. China and Russia have not. The accords do not have the legal force of a treaty, and they do not resolve the deepest questions about resource rights and governance on other worlds. But they represent a recognition that the legal and political framework for human expansion into space needs to be developed proactively rather than reactively, before the conflicts arise rather than after. These governance questions connect directly to one of the most philosophically interesting dimensions of the Mars project, the question of what kind of society a Mars colony would be. Who leads it? Who makes decisions? How are disputes resolved? What rights do settlers have? What obligations do they bear to each other and to the Earth-based organizations or governments that funded their journey? What happens when the interests of the settlement diverge from the interests of the funders? These are not hypothetical edge cases. They are questions that any serious Mars settlement would face, and they have historical precedents, some instructive, some cautionary. Every colonial settlement in human history has eventually developed its own interests and identity distinct from the founding power, and the relationship between the settlement and the founding power has rarely remained stable indefinitely. The American colonies and Britain, the Spanish colonies in the Americas, the Australian colonies and the British Crown. In each case, the physical distance and the specific conditions of the new environment produced a divergence of interest and identity that eventually reshaped the political relationship. Mars would be the most extreme version of this dynamic in human history, a settlement separated from Earth not just by political distance, but by 20-plus minute communication delays, by the impossibility of rapid physical intervention, by an environment so specific and so demanding that it would shape the psychology and culture of its inhabitants in ways that are difficult to predict from Earth. The question of Martian governance is one that science fiction has explored extensively and that political scientists and legal scholars are beginning to take seriously as the timeframe for human Mars missions comes into focus. The scenarios range from Mars as a corporate colony, essentially a company town on an interplanetary scale, owned and operated by the organization that funded its development, to Mars as a scientific preserve with governance modeled on the Antarctic Treaty, to Mars as an independent political entity from an early stage, with settlers asserting rights of self-governance that the founding organizations might resist but ultimately be unable to enforce across 55 million kilometers of space. The communications delay alone means that any Earth-based authority trying to govern Mars in real time would find itself fundamentally hampered. By the time a directive arrives from Earth, the situation on the ground may have changed entirely. Effective governance of a Mars settlement would have to be largely local, largely autonomous, and largely based on whatever social contract the settlers themselves develop. This is not necessarily a problem. It may be one of the most interesting opportunities that Mars presents. The chance to deliberately design a society from a relatively clean slate, informed by everything humanity has learned about what works and what catastrophically does not work in human social organization, but unconstrained by the historical accumulation of institutions and habits and vested interests that make social change on Earth so difficult. Mars settlers would face the same fundamental human challenges that have shaped every society in history: how to organize collective action, how to resolve conflict, how to distribute resources, how to balance individual freedom with collective welfare. But they would face them in a context where the design choices are unusually explicit and the consequences of getting them wrong are unusually immediate. A society on Mars cannot afford the kind of dysfunction that advanced societies on Earth sustain through sheer redundancy and accumulated wealth, a political crisis that paralyzes decision-making for months, the kind that democratic societies experience with some regularity, could be lethal in a settlement where decisions about life support, resource allocation, and emergency response need to be made quickly and effectively. The governance structure of a Mars settlement would need to be resilient, efficient, and capable of functioning under the specific pressures of a small, isolated, resource-constrained community in ways that the governance structures of most Earth nations are not designed for. What that looks like in practice, how much democracy, how much hierarchy, how much individual autonomy, how much collective obligation, is one of the genuinely open questions that a Mars settlement would have to work out in real time. The economic model of a Mars settlement is equally unresolved. What does Mars produce that Earth wants? What justifies the ongoing cost of maintaining the supply chain, the communication infrastructure, the political commitment to a settlement tens of millions to hundreds of millions of kilometers away? The Moon has potential economic value in the form of helium-3, rare Earth elements, and as a platform for space-based solar power. Mars has a less obvious near-term economic proposition. Scientific research, geology, atmospheric science, the search for past or present life has enormous intellectual value but does not generate revenue. The export of physical goods from Mars to Earth is essentially impossible given the energy cost of the transit. Intellectual property, scientific discoveries, technological innovations developed under the specific constraints of Mars. These have potential economic value that could flow back to Earth, but it is diffuse and speculative compared to the concrete costs of maintaining the settlement. The most compelling economic argument for Mars in the long run is probably the one that is hardest to quantify: the argument from civilizational resilience. A humanity spread across 2 planets is more robust against existential risks than a humanity confined to one. Asteroid impacts, supervolcanic eruptions, engineered pandemics, nuclear war, runaway climate change. The risks that could threaten human civilization on a planetary scale are real, and they are not vanishingly small on timescales of centuries and millennia. A self-sustaining Mars colony represents a form of insurance against civilizational collapse that has no other equivalent. The value of that insurance is real, but it is also the kind of value that is notoriously difficult to price in conventional economic terms, because you only collect on the insurance if something catastrophic happens, and the beneficiaries of the payout are future generations who have no voice in current investment decisions. This is ultimately one of the deepest tensions in the Mars project. The strongest arguments for going civilizational resilience, the expansion of the sphere of life and consciousness, the advancement of human knowledge and capability, are arguments whose payoffs are measured in centuries and whose primary beneficiaries are people who do not yet exist. The costs are immediate, concrete, and enormous. The people who bear the costs are living now. The people who collect the benefits are not yet born. Convincing current societies to make that investment, not just once but continuously, over the decades needed to establish a genuinely self-sustaining presence, requires a kind of long-term thinking that is genuinely difficult for political and economic systems calibrated to election cycles and quarterly earnings reports. It has been done before. The decisions made by previous generations to build the scientific and technological infrastructure that the modern world depends on, to invest in basic research whose applications were not yet visible, to plant institutional trees whose shade they would never personally sit under, represent exactly this kind of long-horizon thinking. The question is whether the current generation, facing the specific pressures of the early 21st century, can sustain that orientation toward a goal as distant and as demanding as Mars. The answer to that question will not be found in engineering reports or mission architectures. It will be found in the choices that individuals, institutions, and societies make over the coming decades, about what they value, what they are willing to sacrifice, and what kind of future they are trying to build. And perhaps the most honest thing that can be said about Mars colonization, after examining all of its challenges with clear eyes, is this: the question of whether humans can live on Mars is ultimately less interesting than the question of whether humans choose to. Because the technical challenges, formidable as they are the kind of challenges that human ingenuity has consistently risen to meet when the will to do so was present. The limiting factor has rarely been capability, it has almost always been will. What builds that will, what makes the project feel worth the cost and the risk and the sacrifice, is something that science alone cannot provide. It requires a story, a shared understanding of why this matters, who it is for, and what it means for the kind of beings we are and the kind of future we are trying to create. The story of Mars is still being written, And the next chapter, the one that determines whether any human being actually sets foot on that rust-colored surface within the lifetime of people alive today, is being written right now in laboratories and launch pads and legislative chambers and the imaginations of people who look up at a red dot in the night sky and feel something stir. That stirring matters. It has always mattered. It is the thing that got us from caves to cities and from Earth orbit to the moon, and it may yet be the thing that gets us to Mars. But there is one final layer of this story that we have not yet fully explored, one that sits beneath the economics and the governance and the engineering and the psychology and connects all of them to something deeper, the question of what we might find on Mars, not just rocks and regolith and frozen water, but something that would change everything, something that every mission to Mars has been quietly, carefully, rigorously looking for since the first spacecraft reached Martian orbit more than 50 years ago, the question of life, whether Mars is, or ever was, inhabited, and why the answer to that question, whichever way it falls, is arguably the most consequential scientific discovery in human history waiting to happen. If we find life on Mars, even a single fossilized microbe, even a chemical signature that cannot be explained by any non-biological process, even a strand of something that was once alive billions of years ago in a warm, shallow lake that no longer exists, it will be the most important discovery in the history of science. Full stop. No qualification needed. Because finding life on Mars would not just tell us something about Mars, it would tell us something fundamental about the nature of life itself, about how common it is, about how inevitable it might be when the conditions are right, about whether the universe is, at some deep level, biased toward producing living things wherever it gets the chance. Right now, we do not know the answer to that question. We have exactly one data point, Earth, one planet where we know life arose, one example of the chemistry of life, one genetic code, one fundamental biochemistry based on carbon and water, and a specific set of amino acids and nucleotides. From one data point, you cannot draw a trend line. You cannot say whether life on Earth represents something common, something rare, or something so improbable that it happened essentially by cosmic accident in a universe where it almost never occurs. To distinguish between those possibilities, you need a second data point. And the most accessible candidate for that second data point, the place in the solar system where conditions were most Earth-like for the longest period of ancient history, is Mars. The evidence that Mars was once a very different world is now overwhelming and well documented by multiple missions. The Mars Reconnaissance Orbiter, Curiosity, Perseverance, the various landers and orbiters that have studied Mars over the past several decades. Collectively, they have built a picture of ancient Mars that is almost shocking in its contrast with the cold, dry, irradiated desert that exists today. Roughly 3 to 4 billion years ago, during the Noachian and Hesperian geological periods, Mars had liquid water on its surface in quantities that are difficult to fully comprehend. River valleys, carved by sustained liquid flow over long periods, crisscross the ancient southern highlands. Enormous outflow channels, some of them wider than any river on Earth, speak to catastrophic floods that released volumes of water comparable to entire ocean basins over periods of perhaps days to weeks. The northern lowlands of Mars show features consistent with an ancient ocean, a body of standing water that may have covered roughly a third of the planet's surface to depths of hundreds of meters or more. Gale Crater, where the Curiosity rover has been operating since 2012, contains geological evidence of a lake that persisted for potentially millions of years, with chemical conditions that NASA scientists have described as habitable, not necessarily inhabited, but capable of supporting life as we understand it. Perseverance, which landed in Jezero Crater in February 2021, is operating in what was once the delta of an ancient river, the kind of environment where sediment carrying preserved organic molecules and potentially fossilized microbial life would accumulate and be protected from degradation. The rover has been drilling core samples from the ancient lakebed and river delta sediments, analyzing them in place with its onboard instruments and, crucially, caching them in sealed sample tubes that are being deposited on the Martian surface for eventual collection by a future Mars sample return mission. If life ever existed in Jezero crater, the rocks Perseverance is collecting are among the most promising places in the solar system to look for its traces. The Mars sample return mission, a joint NASA and European Space Agency undertaking, is designed to retrieve those cached samples, launch them into Mars orbit using a small ascent vehicle, capture them with an orbiting spacecraft, and return them to Earth for analysis in terrestrial laboratories. The scientific case for returning Martian samples to Earth, rather than analyzing them only with rover instruments, is compelling. The instruments that can be brought to bear on a sample in a laboratory on Earth are orders of magnitude more powerful and more sensitive than anything that can be miniaturized and landed on Mars. The kinds of biosignature detection, the identification of specific molecular structures, isotopic ratios, and chemical patterns that indicate biological origin that would be needed to make a definitive claim about ancient Martian life requires laboratory techniques that simply cannot be performed by a rover. The returned samples would also be available for analysis by researchers around the world using instruments and methods that have not yet been invented, which is one of the strongest arguments for the sample return approach. You are preserving optionality, keeping the samples available for future science. The Mars sample return mission has faced significant budgetary and programmatic challenges as of the mid-2020s, with cost estimates rising substantially from initial projections and the timeline for sample return pushing into the mid-2030s at the earliest. This is frustrating from a scientific perspective because the cached samples are sitting on the Martian surface right now waiting, but the mission architecture, involving multiple independently complex spacecraft working in coordination across interplanetary distances, is genuinely difficult, and the cost pressures reflect real engineering challenges rather than mere inefficiency. What would a positive result actually look like? What kind of evidence would be convincing? This is a question that scientists have thought about carefully, because the history of claims about Martian life is a cautionary tale about the difficulty of interpretation in the absence of definitive data. In 1996, a team of NASA scientists announced that they had found evidence of possible ancient microbial life in the Martian meteorite ALH 84001, a rock from Mars that landed in Antarctica after being blasted off the Martian surface by an ancient impact and eventually falling to Earth. The announcement made international headlines. President Clinton made a statement about it. The evidence included microscopic structures that resembled fossilized bacteria, polycyclic aromatic hydrocarbons that can be associated with biological activity, and magnetite crystals of a form produced by magnetotactic bacteria on Earth. The scientific community's response was skeptical and careful, as it should be. Each of the claimed lines of evidence was examined and debated extensively. Alternative non-biological explanations were identified for each piece of evidence individually. The consensus that emerged over the following years was that the evidence was suggestive but not convincing, that each feature could plausibly be explained without invoking biology, and that the combination of features, while interesting, did not rise to the standard of proof that a claim as extraordinary as extraterrestrial life requires. The ALH 84001 debate is now a case study in how to think about ambiguous evidence for biosignatures, and it has shaped how researchers approach the Mars life question ever since. The standard of evidence required to convincingly demonstrate ancient Martian life is high, and rightly so. Carl Sagan's principle that extraordinary claims require extraordinary evidence applies with particular force here. A convincing demonstration would ideally include multiple independent lines of evidence pointing in the same direction, the elimination of plausible non-biological alternatives, reproducibility across multiple samples and multiple laboratories, and ideally evidence of something that is difficult to explain without biology, a chemical or structural complexity that non-biological processes are unlikely to produce. The discovery of molecular fossils, specific organic molecules like hopanes or steranes that on Earth are produced almost exclusively by biological processes and that persist in ancient rocks, would be enormously significant. The discovery of isotopic fractionation patterns characteristic of biological carbon fixation would be significant. The discovery of structures with the specific complexity of cell walls or membranes would be significant. But there is a complication that is rarely discussed openly in the popular conversation about Mars life, and it matters a great deal. Even if we find compelling evidence of ancient life on Mars, we will immediately face a question that is almost as difficult as the life question itself. Is that life related to Earth life, or is it independently originated? This matters because contamination, both forward contamination, where Earth organisms are inadvertently carried to Mars by our spacecraft, and backward contamination, where Martian material reaches Earth, is a genuine concern that has shaped planetary protection protocols for decades. The exchange of material between Earth and Mars via meteorites is not hypothetical. It has happened repeatedly throughout the history of the solar system. Several hundred Martian meteorites have been identified on Earth, blasted off Mars by impacts, and eventually captured by Earth's gravity. The reverse, Earth rocks reaching Mars, is also physically possible, though the trajectory is less favorable. If life arose on Earth early in the planet's history and was subsequently transferred to Mars on a meteorite, any life found on Mars might be descended from Earth life rather than independently originated. Distinguishing between these possibilities, life that shares a common ancestor with Earth life versus life that arose completely independently, would require comparing the fundamental biochemistry. If Martian life uses the same genetic code, the same handedness of amino acids, the same basic molecular machinery as Earth life, that similarity could indicate common ancestry, or it could indicate that life converges on the same solutions regardless of origin, which would itself be a profound discovery. If Martian life is biochemically distinct, if it uses a different genetic code, different amino acids, different fundamental chemistry, that would be the strongest possible evidence of truly independent origin, of a second genesis. And a second genesis in our own solar system, on the planet next door, would mean that the origin of life is not a vanishingly rare accident, but something that happens readily whenever and wherever conditions permit. The implications for the abundance of life in the universe would be staggering. A galaxy of 400 billion stars, with billions of potentially habitable planets, seeded with life in essentially every suitable environment, a universe teeming with biology, most of it microbial, perhaps some of it complex, perhaps some of it conscious. That possibility, and the inverse, that Mars is and always was sterile, that life arose on Earth, through a process so improbable that it has not happened twice, even in the same solar system, is what makes the Mars life question one of the deepest questions in science. Not just in astrobiology or planetary science, but in the broadest sense. In the sense of what it means to be alive, and how rare or common that condition is in the universe. And here is where the question of human settlement intersects with the question of Martian life in a way that creates a genuine ethical dilemma that the Mars colonization conversation does not always engage with honestly. If we find evidence of extant life on Mars, not fossil traces of ancient organisms but living things, however microscopic, however simple, existing in subsurface liquid water environments or in other protected niches, the ethics of human colonization become significantly more complicated. Introducing Earth's biological complexity to Mars in the form of human settlers and all the microbial ecosystems that human beings unavoidably carry, trillions of bacteria, archaea, fungi, and viruses that constitute the human microbiome would almost certainly contaminate any native Martian biosphere in ways that could not be reversed. The Martian organisms, having evolved in isolation for billions of years, would have no defenses against Earth biology. The outcome could be the extermination of the only independently originated life in the universe that we have ever found, destroyed not maliciously, but as an unavoidable consequence of our presence. This is not a hypothetical concern in the distant future. It is a question that would need to be answered before the first crewed mission departs, and the answer is not obvious. The scientific argument for preserving any native Martian biosphere from contamination is powerful. Almost any scientist would agree that destroying the only known second example of life in the universe would be a catastrophic loss. But the counter-argument is also real, that the long-term survival and flourishing of Earth life, potentially including human civilization, may ultimately require the expansion to other worlds, and that the value of human life and human civilization is not obviously outweighed by the value of microbial life on another planet. These are genuine ethical questions that do not have clean answers. They require exactly the kind of critical, open-minded engagement that serious thinking about Mars demands. And they illustrate something important about the Mars project overall, that it is not simply a technical challenge wrapped in an inspirational frame. It is a genuinely complex undertaking with implications that reach into biology and philosophy and ethics and the deepest questions about what we value and who we are. The search for life on Mars is currently ongoing. Perseverance continues its sample caching mission in Jezero Crater. The ExoMars Rosalind Franklin rover, a joint European Space Agency and originally Roscosmos project, now being redesigned with a different landing system following the exclusion of Russian involvement after 2022, is intended to drill up to 2 meters below the Martian surface, below the depth where ultraviolet radiation and oxidizing chemicals destroy organic molecules, to search for biosignatures in the more protected subsurface environment. The planned Mars sample return mission, whenever it eventually flies, will give Earth's laboratories their first direct access to the most promising samples from the most promising ancient environments on Mars. The answer, yes or no, life or no life, second genesis or lonely accident, is out there, in the rocks of Jezero Crater, in the subsurface ice, in the ancient lakebed sediments that Perseverance's drill has been sampling. The evidence exists. We just have not yet managed to read it clearly enough to be certain, and the uncertainty itself is one of the most powerful arguments for continuing to look, for sending more missions, for returning the samples, for investing in the science that might finally, definitively, tell us whether we are alone in this solar system, because the answer changes everything. It changes how we think about Mars colonization. It changes how we think about the search for life elsewhere in the galaxy. It changes how we think about ourselves, about whether the impulse toward life and consciousness and curiosity and wonder that has brought our species to the point of being able to even ask the question is a cosmic rarity or a cosmic commonplace, whether the universe is mostly empty or mostly alive in ways we have not yet had the instruments to see. And whether or not we find life on Mars, whether the planet turns out to be a second cradle of biology or a sterile but geologically rich world waiting to be understood and eventually inhabited, Mars will teach us things about the history of our solar system, about the conditions for habitability, about the processes that shape rocky planets over billions of years that will advance our understanding in ways we cannot fully anticipate. Science rarely delivers only what it went looking for. It almost always delivers something unexpected alongside it, something that reframes the questions and opens new avenues that were invisible before. The unexpected is, in some ways, the most reliable product of exploration. And Mars has already surprised us multiple times with the evidence of ancient water, with the complexity of its geological history, with the discovery of perchlorates and subsurface radar reflections, and seasonal methane fluctuations that remain not fully explained. Each surprise has been a gift. Each anomaly has been an invitation to look more carefully, to think more deeply, to revise assumptions that had begun to calcify into certainties. That is the spirit in which Mars should be approached, not as a problem to be solved and a destination to be reached and then exploited, but as a world to be understood. A place with its own history, its own complexity, its own secrets still to yield, a place that will shape the humans who go there just as surely as they will shape it. And speaking of being shaped, the humans who eventually live on Mars will face something that no human being has ever faced before, at least not in this specific form. The experience of being truly, completely, irreversibly cut off from the world that made them, of looking up at a night sky where Earth is just another bright dot, blue-white and impossibly distant, carrying everyone they have ever loved, every piece of music ever written, every work of art ever made, every meal they ever enjoyed, every morning they ever woke up to with sunlight, the right color and air they could breathe without a machine. What that experience does to a person, not in the psychological challenge sense we have already discussed, but in the deeper, philosophical sense of what it means for identity and belonging and the human relationship to home, is something that no amount of research or simulation can fully predict. It is something that will only be known by the people who live it, and they will live it. Sometime in the coming decades, whether it is the 1930s or the 1940s or the 1950s, whether it is a NASA crew or a SpaceX mission or a Chinese taikonaut or some combination of all of these, a human being will stand on the Martian surface and look up at that blue dot and feel something that no human being has ever felt before. Something that does not have a name yet, because the language for it does not exist, because it has never needed to. What they feel in that moment and what they do next will be the beginning of a story that makes everything we have discussed in this video look like the prologue, and the prologue, as you now know, is already remarkable enough. But there is one more thing, one more dimension of the Mars story that ties everything together and that sits at the very heart of why any of this matters, not just scientifically, not just technologically, but humanly. The question of what going to Mars says about us, about the kind of species we are, about whether the impulse that drove our ancestors out of Africa and across oceans and into the sky is still alive in us, still capable of generating the sustained, collective, multi-generational effort that something like Mars requires. The answer to that question is not written in mission plans or engineering specifications. It is written in what we choose to do next. And what we choose to do next is still very much up to us. That is exactly where we are going in the next part, and it is the part that in some ways matters the most. There is a version of the Mars story that is purely technical, rockets and radiation shields and hydroponic farms and nuclear reactors and orbital mechanics. That version is real and it is important, and we have spent a significant amount of this video inside it, because the technical reality of Mars is what determines whether any of this is physically possible, and physical possibility is the foundation everything else rests on. But there is another version of the story that sits underneath the technical one, older and quieter, and in some ways more fundamental. It is the story of why human beings explore at all, why we have always, in every culture and every era, sent people toward the horizon even when the horizon was dangerous and the outcome was uncertain and the cost was real. Why the impulse to go, to see what is there, to understand it, to be present in it, seems to be as deeply wired into our species as language or tool use, or the capacity for grief, understanding that impulse is not a digression from the Mars conversation. It is the Mars conversation at its deepest level, because without it, nothing else makes sense. The technical challenges are solvable in principle, the economic challenges are navigable in principle, but none of the solutions matter if the will to pursue them is not there, sustained and serious and culturally embedded across the timescales that Mars demands. And the will comes from somewhere specific. It comes from the same place it has always come from curiosity, from restlessness, from the particular human discomfort with not knowing what is on the other side of the mountain, the ocean, the atmosphere, the distance between stars. We are not the fastest animals. We are not the strongest. We do not have the best senses, the most efficient metabolism, the most robust immune system. What we have, the thing that distinguishes us from every other species that has ever lived on this planet, is the ability to imagine a future different from the present and then deliberately act to bring it into existence. The ability to hold a model of the world in our minds, identify the gap between what is and what could be, and then organize collective action across time and space to close that gap. That capacity is what built cities and wrote symphonies and discovered the structure of DNA and put 12 people on the moon, and it is what will, eventually, put people on Mars. Not because Mars is easy or safe or economically obvious, but because it is there and we are the kind of thing that goes. The history of exploration on Earth is not a clean story. It is full of catastrophe and cruelty and exploitation alongside the genuine discovery and the real courage. The European exploration of the Americas produced some of the worst atrocities in human history, alongside some of the most remarkable feats of navigation and endurance ever achieved. The history of Antarctic exploration includes both the sublime heroism of Shackleton's survival journey and the senseless tragedy of Scott's fatal race to the pole. The history of high-altitude mountaineering is littered with brilliant people making decisions that killed them and others. Exploration is not inherently noble, it is inherently human, which means it contains the full range of human possibility, the magnificent and the terrible, often tangled together in ways that resist clean moral sorting. Mars will not be different in this regard. The people who go will be capable of great courage and great selfishness, of profound insight and serious error, of building something extraordinary, and of making decisions that future generations will look back on with bewilderment or horror. That is not a reason not to go. It is a reason to think carefully about how to go, what values to carry, what frameworks to build, what lessons from Earth's history of expansion to apply, and which cautionary examples to remember. The Mars project is not a chance to escape human nature. It is a chance to apply human nature in a new context with the benefit of everything we have learned about what happens when powerful people encounter vulnerable populations, about what happens when short-term economic incentives override long-term ecological and social considerations, about what institutions and norms and cultural practices tend to produce flourishing and which tend to produce suffering. The people most likely to go to Mars in the early missions will be highly selected, technically skilled, psychologically resilient, physically healthy, probably young, probably willing to accept risks that most people would not consider reasonable. They will be in some respects extraordinary people, the way the early astronauts were extraordinary, not perfect, but specifically capable in ways that the mission demands. But the goal of Mars colonization, if it is genuinely colonization rather than just exploration, is eventually to make Mars a place where ordinary people can live. People who are not extraordinary in any particular way, who did not volunteer for a dangerous mission, who were simply born there or moved there for reasons that had nothing to do with the romance of being a pioneer, people for whom Mars is just home. That transition from extraordinary mission to ordinary life is one of the most underappreciated challenges in the Mars colonization picture. And it is also, in a sense, the measure of success. A Mars settlement that can only sustain itself by continuously recruiting extraordinary volunteers from Earth is not really self-sustaining. A Mars civilization, if that word is ever to apply, is one where being Martian is not a heroic identity, but simply a fact of life, the way being human is simply a fact of life for the rest of us, where the challenges of the environment have been sufficiently managed that they are a background condition rather than a daily emergency, where children grow up knowing Mars as normal, as home, as the place where life happens, with Earth as the distant blue dot their grandparents came from. That future is not close, but it is also not obviously impossible. And the distance between not close and impossible is where everything interesting lies. Let's talk about what the immediate future actually looks like, not the distant civilization scale future, but the next decade or two, the specific missions and technologies and decisions that will determine whether the longer future is possible at all. Because the next 20 years of Mars exploration are going to be decisive in ways that the previous 50 years were not. Previous Mars missions, extraordinary as they have been primarily scientific, learning about Mars, understanding its environment, characterizing its resources. The next generation of missions is beginning to shift towards something more operational, toward testing not just whether Mars can be understood, but whether it can be inhabited. Perseverance's MOXIE experiment, which we discussed earlier, is an example of this shift. It is not a science experiment in the traditional sense. It is a technology demonstration, a test of whether a specific approach to resource utilization works under real Martian conditions. The Ingenuity helicopter, which flew on Mars for the first time in April 2021 and completed dozens of flights over the following years, demonstrated aerial reconnaissance capability that could be transformative for future mission planning, identifying safe landing sites, scouting terrain ahead of rovers, potentially delivering small payloads to locations inaccessible to surface vehicles. These are operational capabilities, not just scientific instruments. NASA's plans for the Moon under the Artemis program include testing of surface power systems, life support technologies, in-situ resource utilization for water ice extraction, and long-duration surface operations in an environment that is in some respects a useful analog for Mars, airless, radiation-exposed, requiring closed-loop life support, while being close enough to Earth for rapid response if something goes wrong. The specific technologies being developed for lunar surface operations, compact nuclear fission reactors, advanced spacesuit systems, habitat designs for long-duration surface stays, are the same technologies that Mars missions will require, adapted for Mars-specific conditions. The Moon is not just a destination, it is a testbed, a place to find out what breaks, what works better than expected, and what needs to be redesigned before you commit to using it on a mission where the nearest repair facility is a minimum of 6 months away. SpaceX's development of Starship continues on a trajectory that will, if successful, fundamentally change the economics of access to space in ways that matter enormously for Mars. The key enabler is not any single capability, but the combination of full reusability, large payload capacity, and methane propulsion that can be produced on Mars. If Starship achieves its design goals, and the pace of testing suggests that while the timeline is uncertain, the technical approach is sound, the cost of delivering mass to Mars could drop by 1 to 2 orders of magnitude compared to conventional expendable rocket architectures. That cost reduction does not make Mars easy, but it makes it possible to contemplate sending the kind of mass, hundreds of metric tons of infrastructure per launch window, that a serious settlement program would require. The 2020s and early 2030s will likely see the first uncrewed Starship missions to Mars, aimed at demonstrating the landing of large payloads on the Martian surface and beginning the deployment of infrastructure. The challenges of landing large, heavy spacecraft on Mars are distinct from anything previously accomplished. The Martian atmosphere is thick enough to create significant heating during entry, but thin enough that parachutes alone cannot slow a heavy vehicle sufficiently for a safe landing. A challenge engineers call the mid-range problem, and it is one that NASA's Mars exploration program has been working on for years, through programs like the Low-Density Supersonic Decelerator and the Hypersonic Inflatable Aerodynamic Decelerator. SpaceX's approach for Starship involves a combination of aerodynamic body shaping and propulsive landing, using the vehicle's engines to perform a final deceleration burn close to the surface, the same basic approach used to land Falcon 9 first stages on Earth and at sea, but adapted for the much thinner Martian atmosphere and the different gravitational environment. The precision required for landing on Mars is also greater than for Earth landings because the landing site matters enormously. You cannot land a large habitat randomly and then figure out where you are. You need to land within reach of pre-deployed infrastructure, power systems, water extraction equipment, propellant production facilities that were sent on earlier missions. The guidance and navigation systems required for this level of precision on Mars, where you cannot rely on GPS and where the communication delay prevents real-time ground support during the critical final minutes of descent, represent a significant engineering achievement that is still being developed and demonstrated. The human factors work continues in parallel. Analog mission simulations are providing data on crew dynamics, habitat design, operational protocols, and psychological support strategies. The lessons from the International Space Station, where astronauts have now accumulated an enormous dataset of long-duration spaceflight experience, including missions of up to a year or more, are being applied to Mars mission planning. The medical research program associated with ISS continues to advance understanding of the physiological effects of microgravity and radiation, even though the Mars-specific questions about partial gravity cannot be answered until humans are actually in a partial gravity environment. What emerges from all of this work, from the engineering and the biology and the psychology and the economics and the ethics and the philosophy, is a picture of an undertaking that is genuinely, almost incomprehensibly difficult, but not impossible. That is in some ways the most important thing to hold on to, not the inspirational version which papers over the difficulty, not the cynical version which dismisses the goal as fantasy, but the honest version which acknowledges both the difficulty and the real, documented, concrete progress being made toward overcoming it. The difficulty is real, the radiation is real, the gravity problem is real, the psychological isolation is real, the agricultural challenge is real, the medical constraints are real, the economic and political obstacles are real. None of these have been solved in the sense of being reduced to routine engineering problems with known solutions. They are all active areas of research with genuine uncertainties remaining. Anyone who tells you that Mars colonization is straightforward or imminent or just a matter of political will is not giving you the full picture, but the progress is also real. The Mock-C demonstration is real. The water ice maps are real. The Ingenuity flights are real. The Starship development is real. The growing body of knowledge about human physiology in space, about closed ecological life support systems, about radiation medicine and pharmaceutical countermeasures and habitat design for psychological well-being, all of it is real and all of it is advancing. The gap between where we are and where we need to be is real, but it is a shrinking gap, not a static one. The people working on these problems are among the most talented engineers and scientists of their generation, and they are making progress in ways that are not always visible in the public conversation about Mars, but that are documented in the scientific literature and in the performance of actual hardware tested in actual conditions. The timeline is uncertain, the exact shape of the path is uncertain, which specific approaches will work and which will require redesign is uncertain. But the direction of travel toward a human presence on Mars within the lifetimes of people alive today is, on balance, more likely than not. Not certain, not guaranteed, but more likely than not. And that is a remarkable thing to be able to say about a goal that, when the first Mars rovers landed, seemed almost impossibly distant. What will it feel like, that first day? Not the landing will be controlled chaos. Adrenaline and checklists and the overwhelming relief of being alive after the most dangerous 6 months of your life. But the day after, the first ordinary day on Mars, when the novelty of being on another planet is still present but no longer quite so acute, when the work begins in earnest, the habitat checks, the resource monitoring, the instrument calibration, the first careful steps outside in a suit that is keeping you alive against an environment that would kill you in seconds. The first morning on Mars, where you look out the viewport at the rust-red landscape under the butterscotch sky and the smaller, fainter sun, and you think, not with awe, because awe is for the first moments, but with something quieter. Something like recognition. This is where I am. This is real. This is my world now. That moment of recognition, when the extraordinary becomes the ordinary, when the alien becomes home, is the moment that Mars colonization actually begins, not with a rocket launch, not with a landing, but with a human being accepting, in the deepest psychological sense, that they are somewhere new and deciding what that means for who they are. Every explorer who has ever gone somewhere genuinely new has had that moment. The first people to overwinter in Antarctica, the first crew to stay on the International Space Station for 6 months, then a year. The experience of that transition, from visitor to inhabitant, from tourist to resident, from explorer to settler, is one of the most profound psychological events a human being can undergo. And it changes you. It changes what you notice, what you value, what you miss, and what you discover you did not miss as much as you expected to. What the sound of silence sounds like, what the color of the sky means. The people who go to Mars will be changed by it in ways that they cannot anticipate, because no one has been changed by Mars before. They will come back, some of them eventually different, and they will tell us things about what Mars does to a person that we cannot know until someone has been there. Just as the astronauts who went to the moon came back with what the psychologist Frank White called the overview effect, that profound, reportedly transformative shift in perspective that comes from seeing Earth whole and small and blue against the black. The people who go to Mars will come back with something of their own. Something that does not have a name yet. Something that might change how the rest of us see ourselves and our planet and our place in the universe, because that is what exploration has always done at its best. Not just added to the map, but changed how we see the parts of the map we already knew. Mars is not just a destination, it is a mirror, a way of seeing Earth differently by seeing something that is not Earth. a way of understanding what life is by seeing a place that may or may not have had it, a way of understanding what home means by going somewhere that is not home, and in the going, in the difficulty and the danger and the beauty and the discovery, in the daily work of keeping a settlement alive in an environment that wants it dead. In all of that, something genuinely new will be created, not just a base on another planet, but a new chapter in the oldest human story, the story of the species that could not stop wondering what was over the next horizon, that kept going even when the going was hard, that looked up at the night sky and felt not diminished by the scale of it, but invited, drawn forward, called. We have always been called by the distance. Mars is just the latest distance to answer. But even as we look outward, toward the red planet, toward the challenges and the promise of what it would mean to live there, there is something profound happening closer to home that deserves our full attention, something that will shape every aspect of the Mars project, something that is right now changing the way we understand not just Mars but the entire solar system and our place within it. The technology we are developing for Mars, the life support systems, the closed-loop resource cycling, the renewable energy solutions, the understanding of what human beings need to survive and flourish in a resource-constrained environment is not just Mars technology, it is Earth technology. It is knowledge that feeds back into how we manage our own planet, our own biosphere, our own increasingly pressured relationship with the environment that made us. The circular economy principles that a Mars settlement would be forced to apply out of sheer survival necessity, nothing wasted, everything recycled, every calorie of energy accounted for, are the same principles that Earth's civilization is going to need to apply on a global scale over the coming century. Mars and Earth are not separate problems. They are the same problem, seen from different angles, and the solutions developed for one will illuminate the other in ways that are already beginning to emerge from the research programs around space agriculture, closed-loop life support, compact nuclear power, and resource extraction from extreme environments. The investment in Mars is in this sense also an investment in Earth. Not as a justification for the expense, the investment can be justified on its own terms, but as a genuine co-benefit that connects the cosmic ambition of Mars exploration to the immediate, urgent challenges of maintaining a livable planet for the 8 billion people who are already here. That connection between the distant and the immediate, between the grand scale of cosmic exploration and the specific, daily challenge of being human on a planet with finite resources and a fragile biosphere, is one of the things that makes the Mars story not just exciting but important, not just for the people who will eventually go, but for all of us who are, in a very real sense, already living on a spaceship, one with better air and water and gravity than Mars, but one that is just as finite, just as dependent on closed-loop systems, just as vulnerable to the failure of those systems as any Mars habitat will be. Earth is our life support. Mars will teach us to see it that way. And that lesson, if we are paying attention, if we are taking seriously what the Mars project actually requires and what it actually reveals, may be the most valuable thing that going to Mars gives us. Not the discovery of ancient life, extraordinary as that would be, not the expansion of human civilization to a second planet, important as that is, but the clarity, the perspective, the specific, hard-won understanding of what it takes to keep living things alive in a universe that is, on balance, indifferent to whether they survive. We are not indifferent. That is the whole point. We are the part of the universe that cares about its own existence, that asks questions about where it came from and where it is going and what it means. That looks at a red dot in the night sky and feels something move in its chest. That builds rockets and writes equations and grows food in sealed chambers under artificial light and sends its most capable people into the most hostile environment imaginable, not because it is safe or easy or economically rational, but because it matters. It matters. And the next part of this story, the part that addresses what we know right now, today, about the state of the Mars effort and what the next steps look like in the most concrete, specific, near-term sense, is where everything we have discussed comes into focus as a single coherent picture. A picture that is both more difficult and more hopeful than any simplified version of the Mars story you have ever been told. Let's get specific, because the Mars conversation has a tendency to drift toward the abstract, toward grand visions and civilizational arguments and philosophical reflections on the human condition in ways that can make the actual near-term reality feel vague and distant. But the near-term reality is neither vague nor distant. It is concrete and documented and unfolding right now in laboratories and launch facilities and mission control rooms and the offices of space agencies on multiple continents. The next decade of Mars exploration has a shape, not a certain shape. Timelines in space exploration are notorious for slipping, and the history of Mars missions includes enough failures and delays to make anyone cautious about confident predictions, but a shape nonetheless. A set of missions and technologies and decision points that will determine whether the longer-term vision is possible. Start with what is currently operating on Mars right now. As of the mid-2020s, the active Mars missions include NASA's Perseverance rover in Jezero Crater, which has been operating since February 2021 and has drilled and cached dozens of rock core samples from some of the most scientifically promising ancient environments on the planet. Perseverance carries the MOXIE oxygen production experiment, which has demonstrated that producing breathable oxygen from Martian carbon dioxide is not just theoretically possible, but practically achievable with hardware that survives the journey and operates under real Martian conditions. The rover also carries the Ingenuity helicopter, which exceeded every expectation set for it. Originally designed as a 30-day, 5-flight technology demonstration, it flew dozens of times over nearly 3 years before ending its mission in January 2024, when damage to a rotor blade sustained during a landing made further flight impossible. Ingenuity proved that powered, controlled flight is possible in the Martian atmosphere and opened an entirely new paradigm for Mars surface exploration. Also operating in Mars orbit are several spacecraft from multiple agencies. NASA's Mars Reconnaissance Orbiter, which has been in operation since 2006 and continues to return extraordinary high-resolution imagery and radar data about the Martian surface and subsurface. The MAVEN Orbiter, which studies the Martian upper atmosphere and the processes by which Mars is losing atmospheric gas to space. The European Space Agency's Mars Express, operational since 2003 and still returning valuable data. The ESA and Roscosmos Trace Gas Orbiter, which has been searching for atmospheric methane and other trace gases since 2016. The HOPE orbiter from the United Arab Emirates, which arrived in 2021 and has provided new insights into Martian weather patterns, and China's Tianwen-1 orbiter, which arrived alongside China's Zhurong rover in 2021. This fleet of active missions represents the most comprehensive ongoing study of any planet other than Earth in the history of space exploration. The data they are returning is not just scientifically valuable in isolation, it is operationally critical for planning the next generation of missions, because understanding the Martian environment in detail, the dust storm patterns, the radiation environment, the subsurface structure, the atmospheric variability, is a prerequisite for designing missions that can operate reliably within it. Every year of continued operation adds to a data set that future mission planners will draw on. Every unexpected observation, every dust devil caught on camera, every unexpected radar reflection from the subsurface, every anomalous atmospheric methane reading is a data point that refines the model of Mars that mission designers work from. The next major milestone, and the one that the scientific community is most urgently focused on, is Mars sample return. The current plan, developed jointly by NASA and the European Space Agency, involves multiple spacecraft working together. A sample retrieval lander would land near Perseverance's location in Jezero Crater and deploy a small fetch rover to collect the cached sample tubes. A Mars ascent vehicle would launch those samples from the Martian surface into low Mars orbit, making it the first rocket ever launched from the surface of another planet, a significant engineering challenge in itself. An Earth return orbiter, contributed by the European Space Agency, would capture the sample container in Mars orbit and carry it back to Earth, where it would be recovered and taken to specialized containment facilities for analysis. The Mars sample return mission has faced significant programmatic turbulence. Cost estimates released in 2023 by an independent review board place the total cost of the campaign at between $8 and $11 billion, substantially higher than earlier projections, with a timeline for sample return pushed to the late 2030s at the earliest under the then-current architecture. NASA and ESA responded by directing their teams to develop alternative, faster and less expensive mission architectures that could potentially return the samples earlier and at lower cost. The alternatives under consideration include using commercial launch vehicles and spacecraft, simplifying the sample capture and return architecture, and potentially leveraging Starship's large payload capacity to deliver a more capable sample retrieval lander in a single launch rather than requiring multiple missions. As of the mid-2020s, the revised architecture was still being developed, and the final cost and timeline were not yet established. The pressure to return the samples is real and scientifically justified. The Perseverance sample cache represents arguably the most scientifically valuable collection of extraterrestrial material since the Apollo lunar samples, rocks from a known location, collected from specific geological contexts, from environments identified as potentially habitable, sealed, and preserved for laboratory analysis. Every year they sit on the Martian surface is a year that the most powerful analytical tools in Earth's laboratories are not being applied to them. The delay is frustrating to the scientific community, but it also reflects the genuine difficulty of what is being attempted. Launching a rocket from the Martian surface, capturing its payload in Mars orbit, and returning it safely to Earth is a multi-step operation with no margin for error at any step, and getting it wrong would mean losing the samples entirely. In parallel with the robotic program, the human spaceflight programs of NASA, SpaceX, and China's CNSA are advancing toward capabilities that could enable crewed Mars missions within the next 2 decades. NASA's Artemis program, which successfully flew the uncrewed Artemis 1 mission around the Moon in 2022 and aims to land astronauts on the lunar surface through subsequent Artemis missions, is building the operational experience and the hardware heritage that a Mars program would draw on. The Space Launch System, which powers the Artemis missions, is a powerful but expensive rocket that is not designed for the kind of high launch rate that a Mars colonization program would require. The Gateway Lunar Space Station, planned as a staging point for lunar surface operations, develops experience with long-duration deep space habitation that is relevant to Mars mission planning. SpaceX's Starship program has demonstrated rapid iterative development. The approach of building and testing and redesigning quickly that characterized the Falcon 9 and Falcon Heavy development programs. and has achieved significant milestones including successful full-stack integrated test flights and demonstrations of the propellant transfer technology that is critical for the Mars mission architecture. Starship's development timeline has slipped repeatedly from the ambitious targets Musk has publicly stated, but the underlying technical progress has been real. The question is not whether Starship will eventually work. The engineering fundamentals are sound, but when it will achieve the operational maturity and demonstrated reliability needed to be trusted with human lives on an 8-month journey to Mars from which there is no rescue possible. The qualification process for crewed Starship missions will require a substantial number of successful, uncrewed flights across a range of conditions, extensive ground testing of all life support and safety systems, and likely a period of crewed operations in Earth orbit before any deep space mission is attempted. This is not a process that can be rushed without accepting risks that no responsible program would accept. The history of human spaceflight is very clear on this point. The Challenger and Columbia disasters were both rooted in institutional pressures to maintain schedules that overrode the warnings of engineers who identified specific risks that were not adequately addressed. A crewed Mars mission conducted before the vehicle and systems are genuinely ready would not be courageous, it would be reckless, and the distinction matters enormously. The medical and human factors work continues in parallel. NASA's twin study, which compared astronaut Scott Kelly after his year-long mission on the International Space Station with his identical twin brother Mark, who remained on Earth, produced a rich dataset about the physiological effects of long-duration spaceflight at the genetic, cellular, and organ system level. The findings confirmed and extended what was already known: significant changes in gene expression, telomere dynamics, cognitive function, fluid distribution, and the gut microbiome, while also revealing some effects that were more modest or more reversible than anticipated. The study demonstrated both the value of long-duration ISS missions as a research platform and the genuine complexity of the human body's response to the spaceflight environment. Scott Kelly recovered most of the measured changes after returning to Earth, but the study identified specific areas: vision, cognitive performance, certain aspects of gene expression that warrant continued monitoring and investigation. The pharmacological research program for Mars is advancing on multiple fronts. Countermeasures for bone loss, bisphosphonate drugs that inhibit bone resorption, combined with resistance exercise, have been shown to be effective at reducing bone density loss during long-duration spaceflight and are now standard protocol on ISS missions. Countermeasures for muscle loss are less complete, and the combination of resistance exercise with nutritional interventions continues to be optimized. The radiation protection question remains the most challenging. Pharmaceutical radioprotectants, drugs that could reduce the biological damage caused by radiation exposure, are an active area of research, with compounds like amifostine showing some protective effects in cancer treatment contexts, but no drug has yet been approved specifically for the spaceflight radiation environment, and the partial gravity environment of Mars adds complexity that the ISS research program cannot directly address. The Habitat Technology program has advanced significantly in recent years. NASA's work on inflatable habitat modules, building on the success of the Bigelow Expandable Activity Module that was tested on the International Space Station, has demonstrated that inflatable structures can provide substantial habitable volume while being compact enough for launch. The specific shielding requirements for a Martian surface habitat, including the use of water walls, regolith bags, and potentially polyethylene-based materials that provide effective protection against galactic cosmic rays, are being worked through in ground-based testing programs. The integration of life support systems, including air revitalization, water recovery, thermal control, and fire detection and suppression into habitats designed for long-duration Mars surface operations, is a systems engineering challenge of considerable complexity, and it is being approached through both ground-based testing and incremental demonstration on ISS, and in the future, on the lunar surface. Agriculture for Mars has moved from theoretical to experimental in meaningful ways. The work of researchers like Bruce Bugbee at Utah State University, who has studied plant growth under LED lighting and controlled atmospheric conditions for decades, has produced specific varieties and cultivation protocols optimized for high yield in minimal space with minimal resources. NASA's veggie and advanced plant habitat experiments on the International Space Station have grown multiple crops: lettuce, kale, radishes, chile peppers, tomatoes, in microgravity, demonstrating that plants can grow and produce edible food in the spaceflight environment and generating data on how to optimize the growth conditions. The microgravity environment of ISS is not the same as the partial gravity of Mars, and the atmospheric composition and radiation environment are different in ways that matter for plant physiology. But the ISS experiments are building the knowledge base that Mars agriculture research will draw on. The specific challenge of Mars regolith for agriculture, the perchlorate contamination we discussed earlier, the lack of nitrogen, the poor water retention, is being addressed through research on regolith remediation, on soil amendments that can create a viable growing medium from Martian material, and on hydroponic and aeroponic systems that bypass the regolith entirely and grow plants in water or air with controlled nutrient delivery. The energy cost of running an agricultural system on Mars, lighting, temperature control, atmospheric management, is a significant engineering constraint that pushes toward nuclear power as the only practical energy source at sufficient scale. The compact nuclear fission reactors being developed under programs like NASA's Kilopower project, which demonstrated a small fission reactor operating at 10 kilowatts in ground testing in 2018, represent the most promising near-term power solution for early Mars missions and initial settlement infrastructure. Communication infrastructure for Mars is advancing. The current relay satellite network at Mars, primarily the Mars Reconnaissance Orbiter and the Trace Gas Orbiter, which serve as communication relays for surface missions, provides limited bandwidth that is adequate for transmitting scientific data and telemetry from rovers, but would be wholly inadequate for the communication needs of a crewed mission or settlement. A dedicated Mars communication network, analogous to Earth's satellite communication infrastructure, would be needed to support crewed operations, providing sufficient bandwidth for voice and video communication, data transfer, and emergency coordination. SpaceX has discussed the possibility of extending its Starlink satellite communication network to Mars using the Starship architecture to deploy a constellation of communications satellites into Mars orbit. This would represent a significant increase in communication infrastructure compared to what currently exists, and it would be a natural precursor deployment that could be established before the first crewed missions. The geopolitical dimension of the Mars effort is evolving rapidly. The space programs of the United States, China, Europe, Japan, India, the United Arab Emirates, and a growing number of commercial entities are all advancing in parallel with varying degrees of coordination and collaboration. India's ISRO successfully placed the Mangalyaan orbiter at Mars in 2014, making India the fourth space agency to achieve Mars orbit and the first Asian nation to do so on its first attempt. Japan's JAXA has ambitious plans for deep space exploration. The United Arab Emirates, with the HOPE mission, demonstrated that a nation with no prior deep space heritage could develop and operate a Mars orbiter within a decade of establishing a space program. The democratization of access to space, driven by the reduction in launch costs enabled by reusable rockets and the availability of commercial launch services, is bringing more actors into the solar system, with implications for both the pace of exploration and the complexity of the governance challenges. Within the next decade, roughly between 2025 and 2035, the most likely major milestones include the first landing of large payloads on Mars using SpaceX Starship or equivalent vehicle, the return of the first Martian samples to Earth laboratories, the establishment of a sustained human presence on and around the Moon through the Artemis program, and the first serious design and development work on the specific systems needed for a crewed Mars mission. Whether any human being actually sets foot on Mars within the 2030s is genuinely uncertain. It depends on technical progress, funding decisions, political will, and the absence of catastrophic setbacks that are impossible to predict. But it is within the range of possibility in a way that it was not even a decade ago. The 2040s, on current trajectories, are when a crewed Mars mission becomes more likely than not. Not the beginning of a colony, but the first human presence on the Martian surface. The first tentative steps of a process that could, over the following decades and centuries, build toward the kind of sustained, self-sufficient human presence that this entire video has been examining. Each step is contingent on the ones before it. Each step is uncertain, but the direction is set, the momentum is real, and the people working on the hardest problems, the radiation, the agriculture, the life support, the landing systems, the human factors, are making progress that is documented and real and building on itself in ways that compound over time. We are not yet ready to go to Mars with people. That is the honest answer. But we are getting ready in ways that are serious and substantive and accelerating. The gap between where we are and where we need to be is real, but it is the kind of gap that gets crossed. Not all at once, not in a single dramatic moment, but through the accumulation of solved problems and demonstrated capabilities and accumulated experience. That is the actual texture of how hard things get done. And when it finally happens, when the first human crew descends through that thin butterscotch atmosphere and fires their engines against the Martian surface and feels gravity again after 8 months of floating, it will not feel like a sudden leap into the future. It will feel, to the people who have been working toward it, like the next step in a very long journey that began long before any of them were born and will continue long after all of them are gone. That is how the biggest things always work. Not as a single heroic act, but as an enormous collective project, sustained across generations, larger than any individual or any institution, driven by something in our nature that is older than civilization and more persistent than any obstacle we have yet encountered. And in the final part of this story, we bring everything together. The science and the technology and the psychology and the ethics and the philosophy and the specific near-term realities. We arrive at the question that sits underneath all the others. Not can we go to Mars? Not when will we go to Mars? But what kind of people do we need to be to make it work? And what does trying to answer that question tell us about who we already are? Everything comes back to us. Not to the rockets or the reactors or the radiation shields or the hydroponic farms or the orbital mechanics or the sample return missions or the governance frameworks or the legal treaties. All of those things matter enormously, and without them the Mars project is not a project at all. It is a daydream, but underneath all of them, animating all of them, determining whether any of them get built and funded and tested and launched and operated and sustained across the decades and generations they require, is something that no engineering specification can capture, something that is not a technology and not a policy and not a mission architecture, something that is, in the most literal sense, us. The Mars project is a human project, not just in the obvious sense that humans are doing it, but in the deeper sense that it reflects, more nakedly than almost anything else we have ever attempted, what humans actually are. What we value when the stakes are high enough to make the values visible. What we are capable of when the problem is hard enough to demand our full capacity. What we choose when the choice is genuinely difficult and the outcome genuinely uncertain. Mars is not a mirror in the poetic sense only. It is a mirror in the practical sense. Every decision made about how to pursue it, what to prioritize, what to sacrifice, what to protect, reveals something true about the people making the decision that softer contexts conceal. Think about what it actually takes, not in the abstract. We have spent this entire video in the abstract, mapping the territory, understanding the challenges, appreciating the scale, but in the specific daily human sense of what it takes for a person to sit in a small metal room for 8 months, knowing that the air they are breathing is being continuously recycled and that the water they are drinking was their urine 24 hours ago, and that the nearest other human being who is not in that room with them is tens of millions of kilometers away, and that if something goes wrong in a way they cannot fix, they are going to die. What it takes to get up every day in that room and do the work. To maintain relationships with the 3 or 5 people who are the entirety of your social world. To not be consumed by the fear. To not be paralyzed by the isolation. To keep caring about the mission when the mission is abstract and the discomfort is immediate. What it takes is not superhuman. That is the important thing. The psychological research is clear on this. The people who do best in extreme isolation environments are not people who feel no fear, no loneliness, no frustration, no doubt. They are people who feel all of those things and have developed the internal resources to work with them rather than be consumed by them. People with strong relationships, clear purpose, flexible coping strategies, the ability to find meaning in small things when the big things feel overwhelming. People who are, in the end, more thoroughly human than average, not less emotional, but better at using their emotions as information rather than as weather to be endured. This matters beyond Mars. It matters because the qualities that make a good Mars settler, the resilience, the adaptability, the capacity for sustained collaboration under stress, the ability to maintain perspective and purpose in constrained circumstances, the willingness to invest in collective well-being, even when individual comfort is also demanding attention, are not qualities that develop in the absence of challenge. They develop through challenge, through the experience of being tested and finding that you have more capacity than you knew, through the practice of working with others on problems that require more than any individual can provide, through the cultivation over time of what psychologists call post-traumatic growth, the genuine expansion of capacity and perspective that can follow from experiences of extreme difficulty, when those experiences are navigated with adequate support and sufficient inner resource. The Mars project, in this sense, is not just about Mars. It is about what humanity becomes in the process of attempting it, what capacities we develop, what knowledge we generate, what technologies we build, what institutions we create, what values we articulate and refine, and when we are paying attention, actually live by. The attempt matters independent of the outcome, though the outcome matters too. A Mars settlement that fails after a decade of sustained effort will have generated more useful knowledge and more meaningful human development than a Mars settlement that never gets attempted because the challenge seemed too great. This is not an argument for recklessness. The challenge is not an excuse to skip the careful work, the rigorous testing, the honest assessment of what is ready and what is not. The careful work is the point, the rigor is the point. Getting it right, not just getting there, is the standard to which every aspect of the Mars project should be held. Because the people who go to Mars are not abstractions, they are specific human beings with specific lives, and specific people who love them, and specific futures that will be foreclosed if the mission fails due to preventable causes. The obligation to them is real and weighty, and should never be allowed to dissolve into the grandeur of the larger vision, but the careful work, the rigorous testing, the honest assessment, all of it is already happening. It is happening in the labs studying closed-loop life support, and in the simulation chambers studying crew dynamics, and in the operating rooms studying physiological adaptation to spaceflight, and in the greenhouses studying Mars analog agriculture, and in the legal offices studying the governance frameworks that a multi-planetary civilization will require. The work is real, the people doing it are real, and they are right now, at this moment, building the foundation that the Mars project rests on, not in the dramatic, headline-generating way that rocket launches get attention, but in the quiet, cumulative, essential way that foundations always get built. Here is what we know. Mars had water. Mars had a thicker atmosphere. Mars had, for at least some period of its early history, conditions that were not radically different from the conditions on early Earth. Whether those conditions produced life is the question that defines the next chapter of astrobiology. Whether they can support human life with the right technology, the right preparation, the right sustained commitment is the question that defines the next chapter of human exploration. The answers to both questions are within reach, not today, not easily, but within reach in a way that they have never been before, because the tools and the knowledge and the institutional capacity to pursue them have never been more developed. Here is what we do not know. We do not know whether there was life on Mars. We do not know whether long-duration partial gravity is compatible with human health over years and decades, and particularly whether children can develop normally in 38% of Earth's gravity. We do not know whether the psychological demands of genuine Mars colonization, the isolation, the confinement, the communication delays, the loss of Earth as a sensory reality, can be managed in a way that produces functional, flourishing human communities rather than communities under permanent psychological siege. We do not know whether the economic and political will to sustain a Mars program across the multi-decade timescale it requires can be maintained through the inevitable setbacks and the competing demands on public and private resources. We do not know what we will find. Not knowing is not failure. Not knowing is the situation science always starts from, and the scientific method, the disciplined, systematic, iterative process of asking questions and testing answers and revising understanding in light of evidence, is the tool we have for converting not knowing into knowing. It is the tool that has converted every previous not knowing in human history into the accumulated knowledge that makes the current conversation possible. It will convert the current not knowings about Mars into the knowledge that the next generation of missions and settlers will need. What knowing does, what each piece of genuine knowledge generates, is clarity about the next question. Understanding the radiation environment clearly enough to design effective shielding generates the question of how to optimize that shielding for minimum mass and maximum protection. Understanding the partial gravity physiology clearly enough to identify the specific risks generates the question of which countermeasures are most effective and least burdensome. Understanding the agricultural constraints clearly enough to specify the requirements generates the question of which crop varieties and cultivation systems best meet those requirements in the Martian environment. The questions build on each other, the knowledge accumulates, The mission becomes, over time, more possible with each piece of the puzzle that falls into place, and the puzzle has been falling into place for decades, since Mariner 4 returned the first close-up photographs of Mars in 1965. Cratered, ancient, nothing like the fertile world some had hoped for, and through every mission since, each one revealing more detail, more complexity, more of the specific character of this world that is so like Earth in some ways and so profoundly unlike it in others. The Viking landers in the 1970s, the Pathfinder rover in 1997, the Mars exploration rover's spirit and opportunity in the 2000s, the Phoenix lander at the Northern Pole in 2008, Curiosity since 2012, Perseverance since 2021, each mission a step, each step building on the ones before, the picture of Mars becoming sharper and more complete and more actionable with every year. The picture is now sharp enough that we can see what we are dealing with. Not completely. The surprises will continue because Mars is a complex world, and complex worlds always have more to reveal than any set of instruments can capture, but clearly enough to plan serious missions, clearly enough to design systems that we have reasonable confidence will work, clearly enough to identify the remaining uncertainties and target research to resolve them, clearly enough to say, with genuine honesty and genuine conviction, that a human presence on Mars is not a fantasy, it is a plan, an incomplete plan with significant unknowns still to be resolved, but a plan grounded in real knowledge about a real place, pursued by real people with real capabilities. The plan has a shape. The first phase is the one we are in now: robotic exploration and sample collection, technology demonstration, lunar operations as a proving ground, development of the specific systems needed for human Mars missions. The second phase, probably beginning in the late 2020s or early 2030s, involves uncrewed Mars landing demonstrations at the scale needed for human missions, deployment of initial surface infrastructure, and continued technology maturation. The third phase, crewed Mars missions, probably beginning no earlier than the mid-2030s and more realistically in the 2040s, involves the first human presence on Mars, initially for short surface stays, then for longer durations as confidence in the systems grows. The fourth phase, extending across decades beyond that, involves the gradual transition from mission to settlement, from settlement to colony, from colony to something that does not have a name yet because it does not exist yet. Each phase is contingent on the success of the ones before it. Each phase will take longer than the optimists' project and will encounter surprises that the pessimists did not predict either. That is how complex, difficult, historically unprecedented undertakings work. They do not proceed on schedule. They proceed on the accumulated momentum of people who keep working, even when the schedule has slipped and the costs have risen and the skeptics are pointing to every setback as evidence that the goal was always unrealistic. The Apollo program survived the fire that killed Gus Grissom, Ed White, and Roger Chaffee in January 1967. It survived the political pressure to cancel after the fire, survived the redesign delays, survived the budget pressure, and 29 months after the fire, landed Neil Armstrong and Buzz Aldrin on the moon. The resilience was not incidental. It was the program. It was the people who believed the goal was worth the cost and kept working. Mars will require the same resilience. Almost certainly there will be setbacks, launch failures, mission failures, hardware failures, possibly crew casualties at some point, in a program that extends across decades and involves operations at the absolute edge of human capability. How those setbacks are responded to will determine the program's fate as surely as the engineering does. Programs that respond to failure by learning and adapting and continuing survive. programs that respond to failure by retreating into caution or dissolving into recrimination do not. The culture of a Mars program, how it handles failure, how it distributes credit and responsibility, how it makes decisions about risk, is not separate from the technical program. It is the technical program at the human level where all technical programs ultimately operate. You are part of this story, not in the sentimental sense, though that is also true, in the sense that every person who feels the pull of this question is part of the cultural current that sustains the programs that are pursuing the answer. But in the specific sense that the decisions being made right now in the institutions and agencies and companies working on Mars-relevant technology are being made by people who are embedded in a broader society that ultimately determines the resources available, the political support present, the scientific talent pipeline feeding into the programs, and the cultural value placed on long-term, ambitious, difficult collective undertakings when you understand what Mars actually requires. Not the simplified version, but the full picture, the radiation and the gravity and the psychology and the agriculture and the governance and the economics and the ethics. You understand something important about what kind of society is capable of doing it. Not a society that values only the immediate return, not a society that cannot tolerate uncertainty or failure, not a society that treats difficult questions as threats to be avoided rather than invitations to be engaged. A society capable of Mars is a society that has developed, at some meaningful level, the capacity for the kind of long-horizon thinking, sustained collective action, and honest engagement with difficulty that the Mars project demands. That is not a description of any actually existing society, including the ones that are currently leading the Mars effort. It is a description of a direction, a quality of mind and culture that can be cultivated or eroded, that grows when it is exercised and atrophies when it is not. The Mars project, pursued seriously and honestly, exercises it, forces it, creates occasions for it that would not otherwise exist, and in that sense, the attempt to go to Mars is not just an investment in the future of humanity on another planet. It is an investment in the kind of humanity that is capable of having a future on any planet, including this one. We began this video with a simple question: what would it actually be like to live on Mars? And the answer, as you now know, is harder than you were told, more interesting than you imagined, more human than you might have expected, and more important than most people appreciate. It is a question that contains within it almost every other important question about the limits of biology and technology, about the nature of life and consciousness, about the meaning of home and the impulse of exploration, about what we owe each other and what we owe the future and what we owe the places we go and the things we might find there. Mars does not offer easy answers to those questions. It offers something better. It offers the experience of asking them seriously, of being forced by the specific demands of a specific and extraordinarily difficult environment to think carefully about what actually matters and why, to discover in the process of trying to keep human beings alive on a hostile world what human beings actually need, not just physically but psychologically, socially, spiritually, to learn, by going somewhere utterly new, what is essential and what is contingent about the life we have built on Earth. The harsh reality of actually living on Mars is that it would be extraordinarily hard, harder than any human being has ever lived, more demanding in more simultaneous dimensions than any environment our species has ever inhabited. The radiation alone would require solutions we have not yet perfected. The gravity alone would require physiological monitoring and intervention across entire lifetimes. The isolation alone would test the deepest reserves of psychological resilience that human beings possess. The agricultural challenge alone would require a level of precision and closed-loop efficiency that no farming system on Earth has ever achieved. Put all of those challenges together, layered on top of each other, compounded by the communication delays and the finite resources and the impossibility of rescue if something goes catastrophically wrong, and you have an environment that makes the harshest place on Earth look accommodating. And yet, here we are, a species that has survived ice ages and pandemics and the full catalogue of natural disasters that a geologically active planet on a variable star can produce. A species that has crossed oceans on wooden boats and climbed the highest mountains on Earth and descended to the deepest points of the ocean and lived for over a year at a time in the vacuum of space. A species that has, despite everything, and sometimes in ways that are difficult to explain, managed to keep advancing, keep learning, keep reaching for the next thing that seemed impossible until it was not. Mars is the next thing. It is not the last thing. There is no last thing, which is one of the most encouraging facts about the kind of beings we are. But it is the next thing, the next horizon toward which the restlessness that defines us is pointed, the next question that is worth the full weight of our curiosity and our courage and our collective capacity for sustained, difficult, meaningful work. The harsh reality of actually living on Mars is real. Every challenge we have discussed in this video is real. None of it has been exaggerated or simplified or papered over with optimisms that the evidence does not support. Mars is genuinely, ferociously difficult, and the people who will go there, whenever they go, however they get there, whatever they find when they arrive, will face that difficulty with the same flawed, resilient, curious, stubborn, creative, frightened, determined humanity that has carried our species through every previous impossible thing. They will be scared. They will be homesick. They will make mistakes. They will argue with each other about small things when the large things are too overwhelming to confront directly. They will have moments of despair and moments of transcendence and long stretches of ordinary, unglamorous, necessary work. They will look out at the Martian landscape and feel things that do not have words yet. They will miss rain. They will miss the smell of soil after rain. They will miss the color of Earth's sky. And they will keep working. Because that is what humans do when the work matters. The work matters. Whatever you think about the timeline, about the economics, about the politics, about the ethics, the work matters, the questions matter, the attempt matters. And the fact that you are here at the end of this video, having spent this time thinking seriously about what it would actually take, that matters too. Because the future of Mars is not being decided only in mission control rooms and legislative chambers and engineering offices. It is being decided in the places where people choose what to care about, what to pay attention to, what to invest their curiosity and their concern and their sense of what is worth doing in this short, singular, remarkable time we each get to spend being alive on a small blue planet in an enormous and mostly empty universe. Look up tonight. Find the red dot. It is patient. It has been waiting for us for 4.5 billion years. We are almost ready. If this video changed how you think about Mars, then the video on the screen will hit even harder. We broke down exactly why your body would give out before the first year is even over, the specific ways Mars would shut you down, one system at a time. It is right there on your screen. Click it. You are not going to want to miss this one.